Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 6.2 in the Big Ideas Math Integrated Math 3 textbook. We are graphing rational functions. I said this in 6.1, I believe that the inverse variation stuff really was just a precursor to what we're going to do now. It fits in the rational functions chapter, but it's not really rational functions the way we talk about it here. This is the graphing part of it, at least. And it can get a little complicated looking, it can get a little weird. That's what I'm here for. My plan is to do very tableless forms of graphing, though. I'm sure the lecture portion is going to use table bits, and maybe I can use those table bits to explain how I do it in a tableless format. At least with that basic nature, you know, there's one that uses A, H, and K transformations, and in those transformation versions of them, I can plot as many points under the sun as we'd like to. You'll see how I'm going to do that. There are ones that potentially will get more complicated, and we'll see how they talk about it, and then I'll try and dance around it in certain ways as well. Now, to just give you the heads up on that, when we do the more complicated ones, and I'll even link to videos of some more complicated rational function things, you can tell I don't find every point under the sun. I only find critical points that I need to find, specifically intercepts and maybe reflective points as well. So we'll see how far I go with that. For me, it's just basic nature of what I want to get done, and hopefully you can follow suit with how the book talks about it or how I talk about it. Jump to the description section down below if you'd like to find the PDF of this actual section, as well as, of course, graph paper. I'm going to have the scaled graph paper because these graphs go as tall as they go wide for the most part of what we're looking at. So find those down below, please, and follow the timestamps down below as well. We have 58 problems to do. I have a feeling this is going to be a longer video, so buckle in, strap up, whatever you call it, strap in. Let's go ahead and get started. We are going to graph simple rational functions, which to me looks like, well, that's before translated ones. This to me refers to probably just the a value, just vertical stretch, if we call it that. It depends on what they want to call it in this case. It's technically one, but there's much more to it than that. Translate simple rational functions, which to me has the HK stuff involved as well, and graph other rational functions. Now I'm seeing this as something that can be more complicated. We'll see how deep they get, given that they're only doing one section of it. I doubt they get super deep on them, but they can get super deep. I tell you guys, these graphs can look really weird. All right. Now my face right now is hiding what the current nature of these graphs will look like. I'll reveal it to you in just a moment, unless you downloaded it and you already know. A rational function has the form f of x equals p of x over q of x, where p of x and q of x are polynomials and q of x can't equal 0. Listen, you can't divide by 0 here, but rational functions is all about dividing a function by another function. Now, in the case of this being a polynomial, we're talking about this thing having variables in it. So that's where inverse variation is some version of a rational function, because we're dividing some constant variation by a variable. And that's what's going to happen here. The inverse, I should keep reading. The inverse variation function f of x equals a over x is a rational function. So this is an example one with the variable there. The graph of this function when a equals 1 is shown above. So here is what our graphs will, for the most part, look like. It gets really confusing. We'll see if we can make sense of why this graph looks the way it does and how the majority of the graphs will look this way. Some won't. But what's going on here? All right, parent function for a simple rational function. This is 1 over x. Now keep in mind, they're not actually using a table here. They could, but think about what happens when you substitute certain values for x. When I substitute 1 for x, 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 3 is 1/3. 1 divided by 4 is a quarter, etc. When you divide by negatives, 1 divided by -1 is -1. 1 divided by -2 is -2. By the way, what I'm doing right here is a good instance of how I'm going to get points as well. You divide this value by whatever x you have without needing to write it in the table. Now, there are other points as well that go up this way. Think about, hopefully you know this, 1 divided by 1/2 is 1 times 2, which is 2. 1 divided by 1/3 is 3. So you can imagine that this is when x is 1/2, when x is 1/3. When x is a quarter, we hit 4. So that's where it gets that tall portion as well. Now, I'm going to read what they state before I talk about what about this in betweenness here, because if they talk about it, I want to bring it up with them. The graph of the parent function f of x equals 1 over x is a hyperbola. Ooh, you might not know what a hyperbola is. It's a conic section, which consists of two symmetrical parts called branches. I didn't know that. I never called them branches before. The domain and range are all non-zero real numbers. Any function of the form g of x equals a of x, where a doesn't equal 0, has the same asymptotes, domain, and range as the function f of x equals 1 over x. Okay, So before I get moving forward, let me talk about asymptotes. That is going to be basically this line here and this line here. And I'm making them dotted. I don't know if you can tell. I'm making them dotted lines. We've done asymptotes before, obviously, with exponential functions. They were horizontal asymptotes. Logarithms had vertical asymptotes. Rational functions will tend to have both. Now, vertical asymptotes exist for a very obvious reason. You can't divide by 0. If I substitute 0 in for x here, I'd be doing 1 divided by 0. That is not a defined value. So there is no value when x equals 0. The interesting part about this, though, is as x gets really close to 0 from the positive side, like 0.0001, do 1 divided by that number and it becomes hugely positive. Whereas if you go to the negative side of it just slightly, negative 0.0001 for x, you get like negative a billion instead. So it shoots off and it shears in that direction like that. It's kind of doing that thing in that form, and it approaches the asymptote, but of course never touches it. So we're going to have vertical asymptotes in any case where, remember, we can't divide by 0. We can't divide by 0. So this is going to be a big talk of all rational function things that we do, even in the algebra format. You got to figure out where your vertical asymptotes exist based on that. When we get to more complicated, well, I don't know if we will, but if you ever get to more complicated rational functions, there are cases where you do 0 divided by 0, which presents holes. I don't know if we're going to have any holes in our graphs. We'll see if we do. Otherwise, vertical asymptotes is when you divide non-zero by 0. Now, what about the horizontal asymptote? Well, the horizontal asymptote is here for the same reason why they are for exponential functions. There's no value of x I can substitute into here to get 0 for y. Think about it. X can become super large like a billion, but 1 over a billion, although being really close to 0, still ain't 0. And 1 over negative a billion, still really close to 0 from the negative side of things, but still not 0. So horizontal asymptotes are all about end behavior, what we get closer and closer to. It looks like they're talking about actually end behavior right here. As x approaches positive and negative infinity, y is approaching 0, and that's what represents the horizontal asymptote. They actually said it right here. Honestly, I didn't read this. I was trying to find it right here, but they're mentioning here why we have asymptotes in these situations. Now, they mentioned one other thing, guys. We have the same asymptotes, domain and range, no matter what a is, as long as it's not 0, and it won't be. If a is 2, negative 3, positive 10, whatever it is, you're still dividing by 0 in this case, and as x gets really big, you still approach 0 for y. So same asymptotes, therefore same domain and range for those. Okay, so let's look at some of these simple rational functions of the form y equals a over x. This is graph y equals 4 over x, and compare it to y equals 1 over x. So y equals 1 over x is the parent function in blue, as you can see right here, and then the g of x equation is the 4 over x. Now, where does it come from? Well, they're dividing, listen, it's as simple as what you can see here, guys. They are dividing 4 by 1 and dividing 4 by 2 and dividing 4 by 3, etc. Now, I plan on doing that without a table. So 4 divided by 1 is when x is 1, you get 4. That's where that point is. 4 divided by 2, you get 2. So over 2, up 2 like that. 4 divided by 3 is 4/3. I'll be honest, these are ones that you can kind of pass if you'd like to. If it's a fraction and you don't love it, you can get other points, go for it. Like 4 divided by 4. Notice that they don't mention that on here. But 4 over 4 is 1, and that's a point that's on here. I'd rather plot that point than that point any day, just because it's not a fraction. And there are other ones that you could find outside of that. I'm fine with doing like 4 over 8 to get 1/2. I'm fine with like a 1/2. But like 4/3 gets a little messy, and it depends on the numbers. Now in negative land, it does the opposite, right? 4 divided by negative 1 is negative 4. 4 divided by negative 2 is negative 2. 4 divided by negative 4 is negative 1. Yes, I'm skipping the negative 3 there. And you can get those points as well to do the graph. So how does it compare to the 1 over x? It's technically vertically stretched by a factor of 4. This was at 1, now it's at 4. This is 1/2, now it's at 2. It's 4 times taller than it was. They say it lies farther from the axes of f. And they both lie in the same quadrants and have the same asymptotes, domain, and range. Let's see what they say on branches, because I'm not big on that phrasing. Draw the 2 branches so they pass through plotted points. I don't know if we have to describe branches here, but the branches both lie in the same quadrants as these ones. When do they lie in these quadrants? Well, I think you know that answer. Negative values. Negative a values, like this one. We'll probably hit others like that and talk about them then. But anyway, I'm going to circumvent using a table, guys. I can plot as many points specifically as well as they can based off what they have. We will have asymptotes drawn at x equals 0 and y equals 0. I will personally see to it that they are actually drawn. And then, we'll move forward from there. Let's talk about translations with h and k. When they appear in this format, it's the same as they ever were. H is always subtracted from x. This time it's in the denominator. And k is always added to your function, whatever it is. So plus k. So your translation can be HK. Now I intend to graph my functions starting with my asymptotes, vertical and horizontal asymptote, provided that they are in this form, the form that you see here, y equals a over x minus h plus k. So h and k are how far they translate over. That includes the asymptotes. Think about it. You can't plug in h for x because that's when you divide by 0. So where x equals h is where your vertical asymptote exists. Your plus k is the same as it was for exponential functions. It shifts up or down any certain, your horizontal asymptote shifts up or down k units because that's now the k value that we approach and get closer to, but never actually touch. Before it was 0, now it's shifted up or down to that amount. So they say draw the asymptotes x equals h and y equals k. I agree. Plot the points to the left and to the right of the vertical asymptote. I do agree as well. The way I'm going to be doing it is the same as you saw in that in the previous problem. This will basically be my new origin, and I'll divide my a values by 1 and 2 and things like that as I go this way. However many units I go to the right and left of my vertical asymptote is what you're dividing a by. Let's see if we can use this example as this scenario unfolds. Graph g of x equals negative 4 over x plus 2 minus 1. They first draw the asymptotes at x equals negative 2 and y equals negative 1. Keep in mind negative 2 is the opposite of the h that x plus 2, it's negative 2. And the minus 1 is the same. So x equals negative 2 is the vertical asymptote. Remember, it is a vertical line. Y equals negative 1 is there. This to me is my new origin now, okay? Everything I do is in relation to this. I couldn't care less, honestly, about that specific set of points unless we're speaking about intercepts, which I'm not right now. Plot points to the left and right. Now they say, oh, here are some points to plot. Here's what I'm going to do. Remember that this number is a negative 4. This is our a value. First of all, the negative is what's going to get this thing flipping in this direction instead of that direction. Second of all, we're dividing negative 4 by 1 and 2, and I'd rather divide by 4 than 3, things like that. So what's negative 4 divided by 1? Negative 4. What's negative 4 divided by 2? Negative 2. Check it out. What's negative 4 divided by 4? Negative 1. Look, they even skipped the fraction 1. What's negative 4 divided by negative 1? Positive 4. What's negative 4 divided by negative 2? Positive 2. What's negative 4 divided by negative 4? Positive 1. I'm going distance from here. Those are the points. I couldn't care less about what the actual values are. I care about 4 over 1 up, things like that. Dividing your a by that. So this form is brilliant for getting as many points as you'd like. Just do your shift, your translations, and divide this a value by how far off you move from the x-axis. Very nice. Anyway, those are your two hyperbolas. The branches. They didn't ask to compare to a 1 over x equation. Domain is all real numbers except x is negative 2. Range is all real numbers except negative 1. The way I'm going to state that is something like this. Domain, x can't equal negative 2. Range, y can't equal negative 1. We're used to either writing all real numbers or having inequalities, even compound inequalities. This is another version of a domain. You don't have to say x is greater than negative 2 or x is less than negative 2. You can just say x can't be negative 2. That implies all real numbers except negative 2. And same with y can't be negative 1. And that's literally what they're hitting there. Okay, there's this other form. This is where things get a little more complicated. Looks like they're staying basic enough in that these are both still linear functions, but there's still a lot to talk about here. All rational functions of this form can also have graphs that are hyperbolas. They don't just divide and cancel out the x's or anything like that because you have constants that are added to there. So unless you have common factors that cancel out, those x's are kind of staying as they are. They say the vertical asymptote of the graph is the line x equals negative d over c because the function's undefined when the denominator cx plus d equals 0. They're saying literally right here, and I'll probably be doing the same thing, as far as, I'm trying to think if I write domain first or vertical asymptote first. But either way, the vertical asymptote occurs where this thing equals 0. So you subtract d from both sides, and then you divide both sides by c. That's why they're writing this. Now, are we going to have cleaner numbers like negative 4 over 2 to make it negative? Yeah, probably. But we can still draw our vertical asymptote at that x equals equation. Okay. The horizontal asymptote's a little bit trickier to talk about, but it's at y equals a over c. Now this, I'm not going to get really deep into it, but this has to do with a couple things. First of all, these x's being the same degree. they're both degree 1. They're both x to the first power. If this was x squared and this is x to the first power, this ain't a over c anymore. If this was x squared and this is x to the first power or whatever, this ain't a over c. In fact, this one would be at y equals 0. This is all about what's called end behavior. We talked about end behavior. But what happens as x gets really big? As x becomes like a billion and 20 trillion and things like that, this plus b and plus d become rather insignificant with regard to the division. It gets really close to whatever these coefficients are. In terms of dividing, because they're comparing from the same degree. That's as deep as I'm going to get into it, but yes, you do divide this a by this c to get the horizontal asymptote. Now, there's another way to rewrite these, and I'm sure the book's going to talk about it, so I'll wait, but if we do longer synthetic division on this, we can rewrite it in these forms, and then we can do the graphs that way, and maybe, just maybe then, we can talk about why those horizontal asymptotes are how they are with that division. Let's first start with an example of this where it says graph f of x equals 2x plus 1 over x minus 3. State the domain and range. We begin with our asymptotes. First of all, we can't divide by 0, so we solve for what value of x would give us 0 here. That's 3. Therefore, there's a vertical asymptote at x equals 3. These are scaled by 2, so that's 2, 4, and 3's in between. I don't know why they scale by 2's, but they did. The horizontal asymptote is you're dividing 2 by 1. That's because these x's are the same here, and as x gets really large or really small, we get really close to approaching 2 divided by 1. That's 2. So y equals 2 is the horizontal asymptote there. Now, I'll be honest. In cases like these, I don't tend to get very deep in plotting other points. If your teachers ask you to do that, guys, just plug in any points that you can to the left and right of 3 and get what you need to. I would get deep personally. I would get deep in defining the x and y intercepts. And you can reflect points that way if you like to as well. But if I find, unfortunately, these intercepts look like they're going to be fraction values. That's not generally the case. The x-intercept is the value of x when y equals 0, and the y-intercept is the value of y when x equals 0. So for a y-intercept, you substitute 0 for x, and you get 2 times 0 plus 1 over 1 times 0 minus 3. You get negative 1/3. Guess what? That's a point that's on there. Now, why did I plug in that one? Because notice how easy that was to plug in 0. These terms go away. You're just left with the constant values. Very easy to do. The x-intercept is just another joyous set to have because you can have a bunch of these points depending on what kind of graph, how complicated these ones are. These ones will generally only have one x-intercept. But you set 0 equal to, listen, I don't care about the denominator. I care about the numerator. Because the denominator equaling 0 is none of my concern. That's where you get vertical asymptotes. I care about when the numerator is 0. Dividing 0 by something gives me 0. So I subtract 1 and divide by 2. You get x equals negative 1/2. And that apparently is this point right here. Very hard to tell, but that's what we get. Now, is that very many points to plot for this overall thing? No. But do these two give me the idea of where this graph goes? Yes, it does. I'd be on this side of the equation, of the asymptotes, I should say. And then I'll be on this side of the asymptotes as well. There's going to be symmetry involved as long as these are basic, just x's, no squareds, no absolute value, things like that. They'll go as basic as that. If you want to try and plug in another point, guys, go ahead. You can try and plug in 4. Let's see, you get that point right there. And you can find other points that are reflective to that, meaning how this 9 is 7 up from y equals 2. This negative 5 is 7 down from y equals 2. These are both displaced 1 unit away when x equals 4. That's 1 unit away from 3. And when x equals 2, that's 1 unit away from 3. So these 2 points are reflections of each other in a way. And all the other ones would be reflections of each other as well. I'm sure those are the other ones that they're plotting here. So I don't know if they're talking about the reflection piece, but that's something you can do if you want to find your own points. To what extent do you find points is really a good question that I don't know the answer to. That's why we have other versions of how we can do it, and they're talking about it right here. Rewriting a rational function may reveal properties of the function and its graph. For example, rewriting a rational function of the form y equals a over x minus h plus k reveals it's a translation of this with vertical asymptote x equals h and y equals k. So if you can get it into this form again, you can figure out all that information that we spoke on. And I can honestly plot points a lot easier because I can figure out what my a value is based on that. To think that your a value is just 3 would be incorrect. That's not how this thing works. 3 is actually more about the horizontal asymptote, but we'll get into that. So they say rewrite this in this form, which I like that. Rewrite this in this form and graph the function. Describe the graph of g as a transformation of the graph of a over x. So that's probably just going to say, oh, you just translate this many units left and down or whatever it is. So what do? They go to long division. Now, I'm in either or here. You can do long or synthetic. Because it's dividing by a linear function, synthetic's totally fine. It's kind of up to you. They chose long division here, and what they did was they realized, I'm not going to get deep into how long division works, we practiced this already, but you get a quotient of 3 and a remainder of 2. Now, if you remember how that stuff generally would look is, when we're doing, keep in mind, this thing here is a fraction. Dividing it doesn't change the value, it just changes its appearance. Like if I write 6 divided by 3 and I write 2, guys, these are equivalent to each other. It's not like I'm changing what my graph is. So this function can be rewritten as its quotient plus its remainder. And remember, the remainder still divides by this. Now, is this in this form? Not quite. I'd rather flip this, put the quotient last, put the remainder first, because that's just how we tend to have the appearance. And here's the appearance of that in that form. We've seen how these things graph, which is an a vertical asymptote at x equals -1, and a horizontal asymptote at y equals 3. And the way that I would do this is I would start dividing 2 by some numbers. 2 divided by 1 is 2. 2 divided by 2 is 1. 2 divided by 4 is a half. 2 divided by 1/2 is 4. Those are great points to plot. 2 divided by -1 is -2. 2 divided by -2 is -1. 2 divided by -4 is -1/2. 2 divided by -1/2 is -4. Boom. I got some points on that one very specifically, ones that I'd be better off doing as opposed to what we had in the previous one, where getting points are hard to come by and determine which ones are integers and good fractions. 1/2 is good for me, but which ones are good based on that, it's a little hard to figure out. Now, if I use this other version, let's see if everything else pans out the way that we did it from the previous one. Let's start with, well, obviously vertical asymptote is where x is -1. There's no change on that. The horizontal asymptote would be dividing 3 by 1. Y equals 3. Was that so? Yes, it was. Remember, x goes into 3x 3 times. That part of the quotient is your horizontal asymptote. So that's where that comes from, assuming these are both x to the first power, or even the same degree. If they were both x squareds, you could still do the same thing. So we start with those two. Boom, boom. The other points I like to plot are x-intercepts and y-intercepts, right? The y-intercept is by substituting 0 in for x, where you get 5 over 1, which is 5. Do we have a y-intercept at 5? Yes, we do. It's right there. X-intercept is when you solve for x when y equals 0. So you do 0 equals, and you do it with the numerator, 3x plus 5. If you subtract 5 and divide by 3, you get x equals -5/3. Not my favorite point, and it's not really a point that we get to plot. If you'd like to, go ahead, but that's this point right here. That's x equals -5/3. So you can tell where those points do fit in this thing. They do belong. It does seem to rattle off the same way that we just did it here. When you compare it to the f of x equals a over x, you have to realize that our a is still 2 in this case, so it's a translation 1 unit left and 3 units up. Oh, we have word problems. I didn't know that. Okay, so I was wondering why we had 58 questions. I'm like, it's going to be a lot of graphs. It'll probably still be a lot of graphs, but longer lecture. Here we go. A 3D printer builds up layers of materials to make three-dimensional models. Each deposited layer bonds to the layer below it. A company decides to make small display models of engine components using a 3D printer. The printer costs $1,000. The material for each model costs $50. Honestly, I haven't done a lot of word problems with these rational functions solving by graphing. Let's see how to do it. Estimate how many models must be printed for the average cost per model to fall to $90. What happens to the average cost as more models are printed? So, by the way, this is probably a good time to talk about how we did like the inverse variation thing. As the cost, where is it? As the cost per model goes up, the number of models printed goes down. Or vice versa, right? That's how inverse variation works. This is kind of an example of that. The printer costs $1,000 sounds like that is some sort of startup value. I don't know if that's the initial A or how that works. Let's see what they say. Understand the problem. You're given the cost of a printer and the cost to create a model using the printer. You're asked to find the number of models for which the average costs fall to 90. Okay? Write an equation that represents the average cost. So use a graphing calculator to estimate for when it's 90. Okay, so we're going to use graphing calculator for some of these. I'm totally cool with that. They are, so when you are doing a cost amount, an average cost, that's average cost per printer, you have to divide by the number of printers, and that's what we have here. We have the cost of the printer plus the number, the cost of all the units you print. $50 per unit. They said that here. Plus the $1,000 up front. When you divide by M, the cost or the number of printers, you get an average. You get an average. So this is what we're graphing. Now, if you notice, they're showing this rational function here in the graphing calculator. I'm fine letting the graphing calculator do its thing. That's totally cool. If you notice, they are not dealing with negative values. If we did go to the graphing calculator and saw the graph, we would actually get a curve here, and we get a curve here. We don't care about this portion of this curve because we don't care about negative numbers of amounts printed or negative costs or whatever, right? It's all about the positive set, this first quadrant. That's the only thing we care about. We use the trace feature to figure out the average cost to $90 per model. Keep in mind what we're doing is we're trying to figure out for what value of x do we get 90 for y. We're not substituting 90 for x because x is the m. It's the number of that are printed. We got to figure out for what value of x do we get 90. So they said use the trace feature. We can figure that out. Okay, we'll use what we use. So they're getting around there. 25 printed, 25 models. And I guess that's the only answer there. So listen, those might be a little tricky. I might have to talk through that a little bit. I might have to figure it out a little bit myself. We'll see what comes to be when we make those equations what they are. Okay, that's the end of the lecture portion. Very long one. We are going to jump into the vocabulary and core concept check, and then we have up to number 58 to take care of after that. Complete the sentence. Number 1. The function y equals 7 over x plus 4 plus 3 has a blank of all real numbers except 3 and a blank of all real numbers except negative 4. We're talking about our domain range values. The 3 has to do with our vertical shifts for the horizontal asymptote. That is a y equals thing, or what y can't equal. That is actually regarding the horizontal asymptote, so that is regarding the range, what y values we cannot be, except 3. And a domain of all real numbers except 4 is because if I substitute negative 4. If I substitute negative 4 for x, I divide by 0, and that can't exist in your domain. Okay, is this a rational function? Explain your reasoning. I would, I don't know. I guess, in a way, it's not a polynomial. There we go. It's not a polynomial. No, it's not. I don't know what this graph looks like. I'd have to do a lot for it. Probably have to do a table. But no, denominator is not a polynomial. So just because something has variables in the denominator does not automatically guarantee that it's a rational function. Okay. That doesn't mean it can't do rational function-like things. Like there may be, well, I guess there is no vertical asymptote here. There's no way I can get 0. But there may be some forms of things regarding asymptotes and things you could talk about. Doesn't necessarily make it a rational function. It's an interesting one. I don't know what it looks like. And I'm not going to deal with it. I'm going to move forward. Guys, we have numbers 3 through 58 to take care of. Get your, print this graph paper as you like to with me. Get yourself a ruler, probably. We're going to draw those asymptotes all day. I'm going to do the dotted line thing, but I have the line tool for it. So get ready as needed. We're going to do some graphs here. Okay, without further ado, let's go ahead and get started. In exercises 3 through 10, we're going to graph the function. Compare the graph with the graph of f of x equals 1 over x. Okay, if we are intent on comparing to f of x equals 1 over x, here's what I'm going to do. I'm going to graph that first and have that copied and pasted for each problem here. I'll even make it kind of more transparent. I think that'll just work out. But here's the original equation. I just want to get that written. Now, f of x, let's do it in like purple. F of x equals 1 over x will be, let's see what colors I want to stay consistent with. Is orange a good asymptote color? Maybe. Can you really see those? Hopefully you can see those a little bit, but basically these have no translation, so we're going to keep those asymptotes there, okay? Now f of x equals 1 over x is as straightforward as 1 divided by 1 is 1, 1 divided by 2 is 1/2, 1 divided by 3 is 1/3, 1 divided by 4 is 1/4, etc. And it keeps shrinking, getting closer to 0, right? 1 divided by 1/2 is 2, 1 divided by 1/3 is 3. Now we're going x in that direction. You can just see how that kind of works out in that way. It approaches the vertical and horizontal asymptotes like so. I'm going to get these curves looking as good as I can, and then we'll keep these for each problem as we compare this graph to whatever equation we have for each problem. So for this one, I'll have that. Let's see if I can, give me 1 second. I'm just tooling around with this. Let's see if I can copy paste this thing in a way that'll work out for me. Copy, paste, and just flip over here. Hopefully this satisfies the needs of the problem, of each problem here. Okay, that looks like a pretty good deal. So we will keep these two together. Boom. Oh, that moved when I grouped it. Let's try this. Sorry, give me a second. Okay, we'll keep that. We'll make that a little more transparent. Like that, okay. This will stay on every problem that we do. Hope y'all are good with it. And we're going to compare our graphs to this one here. Okay, so keep that one copied. Keep that one copied and off to the side. All right, perfect. So let's start our problems. Y equals 3 over x. This is as simple as me doing this. 3 divided by 1 is 3. 3 divided by 2 is 1.5. I don't love it, but it's still a good point. 3 divided by 3 is 1. I don't like 3 over 4 per se, 3 over 5. 3 over 6 is cool, that's 1/2. And I want to stick to that one so that I talk about what to plot on this other side here. 3 over 1/2 is 6, right? That's a good reminder of getting that. So when we do our description of this graph, I think the way that they said it is it's farther from the axes than the 1 over x, and they're not wrong. Now we have to do the same thing on the other side. It's still truly above it no matter what. I hope you're okay with understanding that. 3 over -1 is -3. 3 over -3 is -1. 3 over -2 is -1.5. You divide by -6, you get -1/2. Divide by -1/2, you get -6. So same thing on the other side, just a reflective version of it, and we get our curve there. So I got everything ready with the 1 over x thing. Obviously, I get to copy paste that each time. I think you'll either have to redraw it or just straight up ignore it, honestly. If you don't want to draw it each time, good on you. I think after these problems, we don't have to compare it. So the graph of G is, I'd like to say vertical stretch by a factor of 3, which is true. But they've been saying the graph of G is farther from the axes than F. They have the same... They lie in the first and third quadrants. They each lie... I think this is going to be the same thing each time. In the first and third quadrants. And have the same domain, range, and asymptotes. Again, that information is not going to change for these problems. For the first ones. Because there's no translations. As long as there are no translations, we're going to have that same information for those parts. You dig? Oops. All right, so that is number 3. Okay, number 4. G of x equals equals 10 over x. Okay, so I get to just copy paste what we had here before. That's cool. This is the 1 over x, f of x we're comparing to. So from here, I get to divide 10 by a few numbers. 10 divided by 1 is 10. 10 divided by 2 is 5. 10 divided by 5 is 2. Notice that I couldn't care less about dividing by 3 and 4. Those are fractions. 10 divided by 10 is 1. So boom, those are points I can plot. 10 divided by -1 is -10. 10 divided by -2 is -5. 10 divided by -5 is -2. 10 divided by -10 is -1. And everything in between hits somewhere along that curve where this is much further stretched out. But this is the exact same information that I can say on this one, because we're not talking about vertical stretches and shrinks, apparently. So the graph of G, again, is farther removed than the graph of F from the axes. Domain, range, asymptotes are the same. They're in the same quadrants together as well. So I can literally copy and paste the other information that we had before, like so. Boom. And boom. No. Ever since, for some reason the copy paste thing is not, there we go. So it's still the same information. There's no change on how we say that versus the other one. Now I have to copy this graph and get ready for number 5. All right, number 5, g of x equals -5 over x. Sometimes you have some numbers that don't divide great, and you know, you do what you do. -5 over x. So, nope, that did not copy. There we go. All right, so -5 divided by 1 is -5. So now this is going in this quadrant here. -5 divided by 2 is -2.5. If I can fit something, I'm going to fit that one. -5 over 5 is -1. -5 over 10 is -0.5. -5 over 1/2 is -10. So I'm going to get those points as well. Get some good points if I can. Without use of a table, I'm good there. And then divide by the negatives, you get positive. Divide by -1, divide by -2, -5, -10, and -1/2. Great points to plot. Already done. Just need to draw the curve. Now this one is farther from the axis than F. However, apologies for the curves kind of being icky. However, they are in different quadrants. They're in the second and third quadrants instead of the, second and fourth quadrants instead of the first and third quadrants. So while I get ready to copy and paste what I'm going to state here before, they have different quadrants that they're lying in. Oh my gosh. I literally hit the copy button. I'm sitting here waiting for it to load. Okay, so they are lying in separate quadrants. I'll just say is reflected in the x-axis. That's what the negative will say to me. It is reflected in the x-axis and has the same domain, range, and asymptotes. Okay. Number 6 would also probably have the same information, so I'm going to get that prepped on the side. All right. So, number 6. We have g of x equals -9 over x. Let's go. Okay. -9 can divide by some numbers. -9 can divide by 1 to get -9. Divide by 2, you'll get -4.5. Divide by 3, you'll get -3. So I'll work that one out. And then divide by 9, you get -1. So those are some. Now, that also means if you divide by 4.5, you'd also get -2. I'm generally not a fan of getting that one because it's just a little weird to talk about, but you still get that point. So maybe for this one, just to find some symmetry in that, you can do it. So divide by -1, you get +9. -2, you get +4.5. -3, you get +3. -4.5, you get +2. You know, I generally don't do that one. Actually, you know, I don't mind doing that one. I divide by 1/2 when I can, right? So that's not bad. It's just if you find any old videos of mine, I generally don't talk about that one. But since there are so few points to get for -9, not bad. If you notice, by the way, I'm doing the half arrow thing, the same thing I did for asymptotes for exponential functions. Definitely not a requirement, and definitely something of habit for myself that I do toward any asymptotes. It's my way of saying I'm getting closer to the asymptotes without actually hitting. So I prepped this other text right here. The graph of g is farther from the axis than f. It is reflected in the x-axis and has the same domain, range, and asymptotes. It's my way of getting tricky quick with it because I'm already almost 40 minutes in. All right, number 7, even farther out. We're just distancing ourselves a little more each time. So 7 is g of x equals 15 over x, and I actually have to copy one of the graphs over here with this. Give me 1 second. Copy. Oh, I cut it. Even better. Paste. Okay. Not actually better. All right, 15 over x. 15 divided by 1 is 15. Can't quite fit it on this graph. So I'm just going to divide it by, you know what? You can divide it by 1.5 and you get 10. How about that? 15 divided by 1.5 is 10. 15 divided by 2, not great. I'm going to fit it just because I am lacking in points. You get 7.5. 15 over 3 is 5. That also means 15 over 5 is 3. And let's try and do some of those ones that we did, right? So now we can go over 7.5 and up 2. 15 over 7.5 is 2, and 15 over 10 is 1.5. So at least I can get some points there. It's quite a bit. Still got quite a bit of points there, and divide by the negatives right here as they reflect over. Divide by 2 is -7.5, or -2. Divide by -5 is -3. Divide by -3 is -5. Oh, divide by -3 is -5. Divide by -5 is -3. Divide by -7.5 is -2. Divide by -10 is -1.5. So, nice points there. Definitely distancing itself farther out. It is 15 times stretched, vertically stretched by a factor of 15. That's truly the way you could describe this if you'd like to, compared to the f of x equation. Still approaching the asymptote, but it's going to take longer to get there. because 15 is just such a large number in comparison. And I'm not changing the scale of my graphs, right? So I don't change. All right. Nothing's wrong with it. I'd literally type the same thing. Still going farther on number 8, not quite as far as 15. I can actually get a lot more numbers from this one as well, though. So, see, tableless is fine. It works out just fine. And by the way, I'm going to keep this tableless mantra up, the same idea with it, when I do the next set 11 through 18. Just we're going to translate first as we go. No, I tried to copy this graph. Please register my copy. Thank you. I apologize when that happens, guys. I shouldn't speak on it, but it's me saying I hit the copy button and it didn't register. All right, here's the original graph. Let's divide negative 12 by 1. We get negative 12. I can't really fit it, but I'll kind of pretend like I do. Negative 12 divided by 2 is negative 6. You can divide it by 3 and get negative 4. Divide it by 4 and get negative 3. That's nice. Now we can divide it by 6 and get negative 2. Divide it by 12 and get negative 1. So that is pretty nice, right? That's a lot of points to kind of hit. Same thing with the negative side. We can get positive 12, etc. And then positive 6 when we divide by negative 2. Positive 4 divided by negative 3. Positive 3 and divide by negative 4. Positive 2 divided by negative 6. And positive 1 when you divide by negative 12. So there is the distancing of that one. Still quite far. And it is a reflection in the x-axis. So let me draw my curves, my half arrows. Find it something to copy and paste from before. And then move on to some problems, which looks like we get closer to the x-axis for the next couple where we have decimals. Not as easy to do the division on those ones, by the way. It's not quite common that we see them. So the fact that they have so very few is probably a testament to the fact that we're not going to have those very often. Let me get one of these set up here, reflected in the x-axis. All right, this one should work just fine, assuming that registered. Let's find out. Yes, it did. All right, graph of G is farther from the axis than F. True. Is reflected in the x-axis and has the same domain range and asymptotes. Yes, we haven't changed any domain range and asymptotes as long as there are no translations. Number 9. Negative 0.5 over x. This is now half of what it was before. So it's going to be a very close graph, and there's nothing I can really do about this that'll make it look good if I keep my scales as they are. And I guess I intend to keep the scales as they are. I don't know if that's being senior lazy or what, but it's just a way of stating, hey guys, these things punch pretty close here. All right, they punch pretty close. So on this set, g of x equals negative 0.5 over x. Now keep in mind, it's just half the distances of these other ones, right? But it is in negative realm. So negative 1/2 divided by 1 is negative 1/2. Take half of a half, and listen, I'm not even going to say negative. We know we're going down, right? So I'm not even going to say negative here. Take half of a half, you get a quarter. Take a quarter of a half, a third of a half, you get a sixth. The quarter of a half, you get an eighth, right? At some point, it just presses closer. There's not much I can say there. When I divide half by a half, I do get 1, though. When I divide half by a third, let's see, a quarter, I get 2, because that's times 4, right? And then times, I don't know, that's quite enough for me, actually. Divide it by 1 here, you get a half, just going to the left, but it's going up, right? And then divide by a half, you get 1. Divide by, or take half of a half, you get a quarter. Divide by a quarter, you get that 2, right? So that's where you get some of those points there. Maybe that one up there and that one up there. And I don't know. There's not much that I can say there. This one, wait, did I mess up here? Divide by, oh, this should be 2 right there. I'm sorry, I messed that up. Okay. So not much in the realm of getting very nice looking points, but there's nothing we can do with that. A table doesn't change it. The only thing that changes a better appearance is scale, which I did not change. The 1 itself is already pretty pressed. No matter what you divide by with a number other than 1, you would still get fractions on those too. Right, it did. That's probably an easier one to divide with. So let's type it differently, I guess, this time. The graph of G lies closer to the axes than F and is reflected across, or in the x-axis. Domain, range, and asymptotes are the same. Okay, I'll get that one ready for the last one. The last one is just not reflected in the x-axis, but okay, number, oops. Yes. Okay, number 10. Yeah, this is going a while, guys. We're going to number 58, right? So number 10, and these are the easy graphs, I guess. But we're doing descriptions. We're doing, I guess the other F is already pre-drawn. 0.1 over X, y'all. These aren't going to have very good points. It's going to be very tight on this. 0.1 divided by 1 is 0.1. Already it's just really close. 0.1 divided by 0.1 is 1. You can just see a nice tight fit here. There's really nothing here I'm going to be able to plot that's of great substance. This thing goes up forever. It goes, right forever, things like that, closer to these asymptotes. It's just hugging really tight to this thing. It's also closer. You divide it by 2, you get 0.05, right? Again, even with the table, you get 0.05. There's no change. There's nothing I'm doing differently in that front. So nice and tight. That's just basically as best as I can fit. As far as talking about this, it lies closer and is in the same quadrants as F. But domain, range, and asymptotes are the same. Okay, guys, that is numbers 3 through 10 and comparing those. Now we're going to start stating domain and ranges instead of comparing them with these translations. So now domain and range are not necessarily the same. Let me grab another set of axes here. Let's do number 11. Now, this is everything I speak of. Listen, there's a reason I do the lecture portion. Everything I speak of is based off what we did in the lecture. G of x equals 4 over x plus 3. Difference is I didn't get to draw the graphs at the time. They did, and I just confirmed that what they drew was correct. So with this one, our a is still that 4. We're going to divide 4 by certain numbers, but this is after we do a certain translation of values. Translation is 3 units up. So your new horizontal asymptote is at y equals 3 instead of y equals 0. The vertical asymptote has not changed. That's at x equals 0. You can tell here that your vertical asymptote should be x equals 0 because you plug in 0 for x, you still divide by 0 there. I want to use a different color. I don't want to use orange anymore. I like green, I think. Green looks better to me. Okay, so now this is like my new origin. So 4 divided by 1 is 4. That's how I'm going to do this. 4 divided by 2 is 2. 4 divided by 4 is 1. Okay. 4 divided by 8 is 1/2. 4 divided by 1/2 is 8. That's 8 up is at 11. Can't really fit it, but I can sort of. And we can divide by the negative. So now we go this many down. So 4 divided by 1 is 4. 4 divided by 2 is 2. 4 divided by 4 is 1. 4 over 8 is 1/2, and 4 over 1/2 is 8. 8 down from -3 is -5. Those are good points to plot. So without use of table, I'm still getting a bunch of very good points. I'm only choosing ones with decent fractions. To me, 1/2 is a decent fraction. I don't like to divide 4 by 6 or 3 or things like that, or 7. That's kind of a random one. I'm dividing by something that makes this look good. And domain and range. Domain, x can't equal 0. Now this is based off the asymptotes as well, but x can't equal 0. Range, y can't equal 3. That's how we're going to state those. In future problems, we might talk about, hey, vertical asymptote is at x equals 0. Horizontal asymptote is at y equals 3. Yes, very true. These are the equations of the lines that we draw for which represents the values we cannot equal. But, just make sure that you understand why we state one versus the other. All right, number 12 is y equals 2 over x minus 3. Same thing as last time. There's only a vertical shift, only vertical translation. Just change there. And it is 3 units downward this time. So 2 over x minus 3. We got ourselves a horizontal asymptote down here now. Vertical asymptote unchanged, x equals 0. And now we divide 2 by certain numbers. Not my favorite. I like bigger numbers like 6 and things like that. 8 and 6 are probably my favorite ones. 2 over 1 is 2. 2 over 2 is 1. 2 over 4 is 1/2. 2 over a half is 4. We could go out to 8. 2 over 8 is a quarter. Not my favorite, but I want to get some other points. 2 over a quarter is 8. 8 up from negative 3 is 5. So that's a quarter way. And same thing here. 2 over negative 1. 2 over negative 2. 2 over negative 4. 2 over negative 8. And then divide by negative a half and negative a quarter, which just falls off at negative 11 there. So, still get my graph on. I lived above the points a little bit. I'll shift these downward just slightly. It's just a little off to me. Just over. There we go. All right. On this side, we got this guy. You're going to have to forgive some of my curves not looking perfect, but the points, I bet I'm getting more points than most people would with a table, at least when I get farther out there. Domain is x can't equal 0. Range is y can't equal negative 3. Okay, now we deal with horizontal translations on 13 and 14. So on number 13, we got 6 over x minus 1. Now suddenly the vertical asymptote changes, right? For the domain, x minus 1 can't equal 0. When you add 1 to both sides, you say x can't equal 1, right? That's the idea behind that domain. Get used to me writing those things out later for the more complicated rational functions. It's just a way of setting it up for ourselves. The range, this a plus k is plus 0. Range already, we can say y can't equal 0. Just get ready for those two. So we have a horizontal asymptote at y equals 0. We have a vertical asymptote at x equals 1. So here's our translation to the right. We basically have this now as our new origin. We get to divide 6 by numbers. 6 divided by 1 is 6. 6 divided by 2 is 3. 6 divided by 3 is 2. 6 divided by 6 is 1. This is 6 away from the vertical asymptote, not from y-axis. So we'll get those ones. Dividing 6 by 12, it kind of falls off to the way. It's a little far away. This other side, I can probably get it a little bit more. 6 over 1 is 6 downward. Over 2 is 3 downward, etc. 6 away from here is at negative 5. That's where we get the 1. 12 away, so this one I can fit probably a little bit more. 12 away is at negative 11, and that's where we get a negative 1/2. So if you want to kind of get one of those points, it's not bad. But it doesn't change the fact you get closer to the asymptote as you move along. Make sure that you do get closer to the asymptote without crashing through it, without flattening out, things like that. It gets closer slowly. Right? You don't have to force it right next to it. Just because I don't have another point here doesn't mean I have to go like this and then boom, right? It actually kind of hits 1/2 up here at 12. You know what I mean? So that's why we try and get more points when we can, but I want you to get the understanding of the rational functions. Now this is all, we did inverse variation on section 6.1. I know we're not really going to look back at that again, unless our word problems kind of tend to lean toward what we did. But, inverse variation kind of spoke on the same stuff. The larger x gets, the smaller y gets, but it never becomes 0. I mean, outside of asymptote changes, but it never, hits the asymptote. It just approaches it. Number 14, y equals, we have a 1. Y equals 1 over x plus 2. I could honestly take one of our old graphs that we did and just translate that over the 1 over x ones, because it's that same thing. Our vertical asymptote's at x equals negative 2 for that shift, right? Shift 2 to the left. So our domain is x can't equal negative 2, right? Keep that in mind. Y equals 0's here. We don't seem to have a vertical shift for that horizontal asymptote. 1 divided by 1. Whoops, let's use blue. We got 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, etc. Divide by a half. You get 2. Divide by a third, you get 3. Divide by a quarter, you get 4. Same thing will happen on the other side. Divide by negative 1, etc. Negative 2, negative 3, negative 4. And divide by negative 1/2, negative 1/3. Whoops. Negative a quarter. Remember, that's x going negative a quarter, and then y becoming negative 4, things like that. So I'm not going to go all the way to the tippy top. I'm just going to kind of push close, draw my half arrows, and be on my merry way. Okay, a lot of concentration there. Domain, x can't equal negative 2. Range, y can't equal 0. Whoops. And remember, that's just a way of saying it can equal anything but 0 or anything but -2, right? That's the statement we're making there. All right. 15 and 16 are quite like 13 and 14 with the horizontal translations, but now a is negative, which just means there's a reflection on the thing. It's no real difference. -3 over x plus 2. We got vertical asymptote again at x equals -2. It's no different. Our asymptotes on this problem are the same as the ones on number 14. There's no change there. Difference is how a changes things, right? It's a vertical stretch by a factor of 3, and it's a reflection in the x-axis if you want to claim them that way. I just divide -3 by these numbers. Numbers that work. -3 over 1 is -3. Keep in mind, we'll just be underneath, okay? -3 divided by 3 is -1. We can divide it by 2, sure. We can divide it by 6. 6 over is at -4, and we get -1/2. So divide by -1/2, or 1/2, and you get -6, like so. Those are good points. Let's do the same thing on the other side. Divide by 1, divide by 3, heck, divide by 2, you get your 1.5. If you want to divide by 1.5, you can get 2. Again, I don't tend to do that one, and it's just those points are so close together, it's probably not worth it. Divide by 6. 3, 6, you get 1/2. Divide by 1/2, you get 6. Boom. Okay. So still a lot of good points. Table be darned. The problems, if you were with me on the lecture portion, the problems that I do concern myself with, where I don't plan on using a table but seeing what points I can fit, are probably the ones that follow this one. I mean, I don't know if they're going to error analysis next or what, but the next core of problems, because we had an example on it, the ones where we have a more complicated appearance and we don't get them in this form, we'll see which points I want to truly decide to plot and not. Because I'm not always going to, oh, there is error analysis after this. I don't always plot every single point like this that I do unless we do that division, which we're not going to be asked to do each time. All right, number 16. How long have we gone? Almost an hour. Okay. Guys, we're not even a third of the way through the problems here. We're about a quarter of the way through the problems. That I don't know if this is going to be a 4-hour lecture, therefore a 4-hour video. But hey, they're as long as they have to be, right? So this one, 7 over, geez. So we're going to go 7 to the right here, which just means I don't get to get many points on one side of this graph, and I get to get a lot of points on the other side. It's still y equals 0 for this thing. So unfortunately, dividing -2 can only bring me so far on this side. -2 divided by 1 is -2, divided by 2 is -1. I can divide it by 4, but even then it doesn't really fit. I can pretend like it does at 11. That's 1/2. And here, divided by 1/2, you get 4. I can divide by 1/4 and get 8. I can still kind of get something on that side as best as I can. It was negative, so we're down in that quadrant area. And on this quadrant, I'll try and fit some more on this side just because I can. Divided by 1 is 2. Divided by 2 is 1. Divided by 4 is 1/2. Divided by 8 is 1/4. How far can I go and make it look good? Can I divide by 16? What's 7 minus 16? -9? Yeah. Divided by 16, I get 1/8. Oh, yeah. Look how far over I'm going. Divided by 1/2, I get 4. And 1/4, I get 8. And that's really to the extent I can go on those. All right, so I get pretty stretched on one side, not so much on the other side. There's still symmetry in the graph. We just can't represent it the same way just because of how far we moved ourselves. Doesn't mean doesn't work. I still want to plot points where I can fit them. And I hope when I'm saying these things out loud, it's making sense because I'm not using a table. I won't use a table. You can. You might be forced to. This is my solution guide video. Okay. There we have that on number 16. Domain x can't equal 7. As we have our vertical asymptote there. Range y can't equal 0. Why can't I equal 0? Well, plug in any value for x. You still don't get 0 for y, no matter what. Numbers 17 and 18 use translations on both. I've been waiting for these. So, not that they're super exciting. It's just that I was like, when are we going to get them? So we have a -3. Hey, it's like number 15 is -3 over x minus 4 and -1. So that new origin, if you will be the intersection of both of these asymptotes, if you will. So I have an asymptote, a vertical asymptote at x equals 4. Remember, it's kind of opposite of that one, but this one's the same. Y equals -1 is my horizontal. And my new origin sits at the intersection of the two asymptotes. That's what I'm going to divide -3 by to get my points. -3 over 1, -3 over 2, heck, -3 over 1.5 if you like, -3 over 3, -3 over 6, -3 over 1/2. Okay, same thing on the other side. Divided by 2, heck, divided by 1.5 if you'd like to. Again, something I didn't used to do. I think now suddenly, now that I started it, you can't stop me now. Divide by 1/2, you get -6. That 1, 2, 3, 4, 5, 6. I can fit, let's see, 12 away. 7, 8, 9, 10, 11, 12. That's now 3 over 12 is a quarter. All right. Looking good, looking fast, right? Plugging in values in a table. Pff, how long would that take? A long time. We lean toward efficiency, partner. Listen, everything I'm doing is correct. These aren't shortcuts. Everything I'm doing is correct, and it's with understanding rational functions as a whole. Plugging in a table, to me, can lack understanding, because now you're just plugging in numbers and just getting points and plotting them. Here, we're actually making use of how these things deal with the functions. That's where I'm saying it. Y can't equal -1. Now we have a change again in horizontal asymptote. Don't forget those. Number 18. So 18 is interesting because of how big this 10 is, yet how far we are going to translate vertically and horizontally, actually. So we'll see what points we can actually fit with this all told. So 10 over x plus 7, and then minus -5. So x plus 7, vertical asymptote at x equals -7. And then -5 here. Make sure that was good. Okay, that was good. All right. So for 10 divided by 1 is 10. 10 up from -5 is +5. 10 divided by 2 is 5. 10 divided by 5 is 2. 1, 2, 3, 4, 5 is 2. 10 divided by 10 is 1. 10 away from -7 is 3. And honestly, I don't know if I have any other good values to hit. I can't go 20 over, things like that. That's just kind of it. This one's going to be very bare bones. I'll divide it by 2 to get -5, or -2, and I'll divide by -5. That's kind of stretched out here to get -2, and really it's just an unfortunate graph when it comes to this. I only plot what I can, and even here I'm way beyond the window range. On this side I get significantly more, but even then I'm not getting specific points on all those ones. It's still good. It still works. It's just, oh my goodness. It's just a little, requires a little more artistry is all. Just note what this thing is doing as a whole as it continues to approach. My stylus on these graphs is wearing thin, and I replaced it. But when I start to do those long ones, it gets a little tough. I am going to stretch this one out more just to see it approach it. There we go. All right, domain. X can't equal -7. Otherwise, we divide by 0. Range. Y can't equal -5 because we never get -5 as a value for y. Okay. Numbers 19 and 20 say describe and correct the error in graphing the rational function. Don't mind if I do. Y equals -8 over x. It's my belief and understanding that they only make one mistake, not multiple. My guess here is the only one is not dealing with that negative. A negative graph would be going in, this direction instead. And I'll go ahead and use their graph for it to keep the scale the same and make sure that it is actually the same. So I'll get this one prepped while I do identify their mistake. They didn't reflect in the x-axis. That's basically all I'm going to say there. This graph, they did not reflect in the x-axis. As far as asymptotes go, they're at x and y equals 0. Those are fine. As far as the points, I think they're all good. I mean, we'll confirm that on this other side. I'll do this one in green. So notice these are scaling by 2s, 2, 4, 6, 8, etc. So -8 divided by 1 is -8, 2, 4, 6, 8. I still want to plot that one. -8 divided by 2 is -4. -8 divided by 4 is -2. -8 divided by 8 is -1. So it looks to be the same graph on this side as it was on the side above it, or to the left of it, because it's all symmetrical. but this thing reflects in the x-axis. I guess technically in the y-axis you could argue as well, to get the graph that we're looking at here. And yeah, we're going to do the same thing on the other side. Divided by -1 is -8. Divided by -2 is +4. +4 is -2. And -8 is -1. So same thing on that side. There's the correction. Same graph with the reflection. Whoopsie. Same graph with the reflection. We got it. What I could have also done is it would have changed, it would have made the numbers go upside down or something like that. But I could have taken this graph and like, hold on. Let's resize it the same way. I could have just like flipped it over. Like flip, boom, and then boom, now it's that graph, right? So if I make it transparent enough, you can see it's supposed to be like that same graph there, right? So hopefully you can see the alignment. Maybe not perfect, but there it is. Okay. That's one of the, I can't even delete. All right, that's one of the errors. Let's go to number 20. 2 over x minus 1 minus 2. If I'm going to make a guess without looking at the graph, I'm guessing they translated the wrong direction. All right, let's see. 2 over x minus 1 minus 2. Yep. So they translated to the left instead of to the right. That's what they tend to do on these translation problems. Rest of the graph is probably correct, but when I correct it, I probably want to make my own this time because there's going to be overlap on this one. We can try it. They translated left instead of right. Now, if I were to explain why that's a problem, I mean, some people still don't know why. You're like, oh, why do we change the sign on x? We flip, we do the opposite of -1 and make it 1. Because what value of x gives you 0 is the important aspect of it. It's the distance from the asymptote. When I plug in 1 for x, I'm dividing by 0. That's why the asymptote is what it is. It's about what you plug in for x, not what h is. It's about what you plug in for x. So what I plug in for x, here's my new vertical asymptote right there. What I plug in for x is, I'll make it thicker, is 1 to make it 0. And dividing by 0 is undefined, and that's where we have that. So this graph, this corrected graph, I'll also do in green. Divide 2 by 1 to get 2, divide by 2 by 2 to get 1, etc. Divided by 1/2 to get 4 if I want to fit it. Divided by negatives, -1 and -2 and -4 and -1/2. And it's basically a translated version of the graph that they have. Just a little bit over. 2 units to the right because they went 1 unit in the wrong direction. So that one, and then this one right here. Analyzing errors and correcting errors. Okay. Number 21 through 24 says match the function with its graph, explain your reasoning. What I'm seeing are the same 2, 3, and 1 values. The 2s are always positive. It's all about our translations. So this is all about which direction they translate. What I will do is I'll just describe. Let me just type this out. It should be faster. I will describe what the translations are, therefore we can get our matches. So 21, 22, 23, and 24. Okay, on 21, we are translating 3 right, 1 up. On 22, we're translating 3 left, 1 up. I hope you can see why this is. On 23, we're translating 3 right, 1 down. And on 24, we're translating 3 left, 1 down. Everything else is the same. The 2 is the same, and the asymptotes based off that. Those are all the same. So at number 21, we have to go 3 right, 1 up. That'll be graph A. These are the reasoning here, right? And then now I'm doing it. Let's go 3 left, 1 up. 3 left, 1 up is C. I mean, these are the asymptotes all the same, but these are translations. 3 right, 1 down is B. And then the last one must be D. 3 left, 1 down. Yep, 3 left, 1 down is D. So I'm actually surprised they didn't do those ones first before some of the other ones so that we can get the understanding of the points that are plotted and such. But that's 21, 22, 23, and 24. All right, those are the 4 quickest problems we're going to have. Now we're going to have probably the 8 slowest problems that we've had. Graph the function, state the domain and range. Now, what I'm looking at right now, 25 through 32, these 8 problems versus these 8 problems, these ones are going to ask us to get it in this form. So we're not being asked to get it in this form right now, which is fine. But I'm not necessarily going to plot as many points as I can fit in the same way because we're not in the form. That form allows me to divide a specific a value by those things, and the a value here is not truly revealed for what I want it to be. If I can determine what it is, then I can carry forward with it, and I'll show you what I mean as far as determining what it is. It's really about when you displace yourself one away from the asymptote, what you're dividing by. We'll talk about it when we get there. In which case, then I could do it. But I'm going to focus on critical features. To me, the critical features in this case are the asymptotes and the intercepts. And then from there, see what we can do. So as far as a vertical asymptote goes, vertical asymptote will be at x equals 3. This is because, again, dividing by 0 in this case. Horizontal asymptote, if you heard me in the lecture or you saw it in the book, as long as these x's are the same, and notice they are always degree 1, degree 1, degree 1, etc. It's not going to change here. As long as they're degree 1, you just divide your coefficients in front. 1 divided by 1 is 1. Y is 1 over 1, which is 1. So we're dividing that one by that one. Not going to get deep into the explanation. If you want to try and plug in big numbers for x, like 100 or a billion or something, you can see as we get closer to 1. We will notice it more when we do the next set of problems. And we do our long division and get our quotient. But we're not there yet. So let's begin with these ones. We get a vertical asymptote, horizontal asymptote. From here, I could find the x-intercept and the y-intercept. The y-intercept's actually easier to do, especially in this form. You set these equal to 0. F of 0 equals, and you get 4 over negative, so negative 4/3. Not a pleasant point, but still a point nonetheless. Without doing a true calculation, I just wrote out the division. That's negative 1 1/3 right here. Now, that does mean, I want to mention this now before I move forward, when we went 3 left, we went 1, 2, 2 1/3 down. So when we go 3 right, we should also be able to go 2 1/3 up. That's actually another point that's on this graph. Do I care about it? I don't know. It depends on what you want. But there is a point that would be on this one for this specific set. X-intercept is when you set y equal to 0, and this is where you might have to technically do more work, but not really. You set the numerator equal to 0. And you solve for x where you get negative 4. So x equals negative 4, 1, 2, 3, 4 is this point right here. That means going, oh, I'm sorry. I did that wrong. Negative 4, 1, 2, 3, 4. It's the actual x equals negative 4. So when I go 7 left, I can go 1 down. When I go 7 right, I can go 1 up like that. Okay. Which is also a testament to what your remainder value is with this. 7 divided by 7 is 1. That means that your a value is technically 7, which means if I want to find more points, listen, you can use the table all you want. If you think you're satisfied with your points, I kind of would be at this point with what I have. I could say, hey, I do this and I do that, and I just draw the general behavior. If you want to find specific points, I now know that because I divided by 7 to get 1, my a value is 7. Now, did I do this in previous problems and some other things? No. My a value is 7, though. So if you want to, you can do 7 divided by 1 to get 7. 7 divided by 2 to get 3.5. 7 divided by 3 is 2 1/3. I mean, that works out. And 7 over 7 is 1. So 7 divided by negative 1, etc. So again, I'm doing literally the same thing as I would be in any other case here. 7 divided by 14 is, a half. So if you want to go all the way out there. You at this point would be using a table, right? You'd say plug in points. Which points are good to plug in? That's hard to tell, right? I'm doing ones where I get integers and good decimals. 3.5 is fine. 1/2 is fine. Those are good decimals. So those are the ones that I'm choosing, and I'm doing it based on noticing my a value. I noted my a value, maybe luckily. Maybe you won't always get the a value. This time I did, by figuring out when I go 1 away what we're dividing by. Now, you could do that in other problems too, right? I could just plug in. If I wanted to plug in one number, I could plug in 4. I could plug in 4 to here. 4 plus 4 is 8. 4 minus 3 is 1. And 8 over 1 is 8. 8 is 7 up from 1. Therefore, my a value is 7, right? You can do more of that. At that point, we might as well do long division on the problem. But yeah, still figured it out. There's the graph. Domain and range. Domain, x can't equal 3. And range, y can't equal 1. They are the vertical and horizontal asymptotes that we stated previously. Okay. Yes, these might take a while. Number 26, or maybe I get to do more speed up on problems as we progress forward. Number 26. Y equals x minus 1 over x plus 5. All right. All right. Vertical asymptote is at x equals negative 5. Horizontal asymptote, we're still dividing 1 by 1 to get 1. So y equals 1. So we got that and that. As far as intercepts goes, I'm going to do y-intercept first. I think it's a faster venture. It's not a great number, but y-intercept, it is a point. It's negative 1/5. You plug in 0 for x, you get negative 1/5. X-intercept, well, it's pretty easy. X minus 1 equals 0, so x equals 1. So x-intercept is 1. So we do have a point that's right here at 1, 0. We have a point, the y-intercept at 0, negative 1/5, which is like that. So not great. If you want to get some other points from here, we're going over 1, 2, 3, 4, 5, 6 to go down 1. So we can go over 1, 2, 3, 4, 5, 6 to go up 1. That's a point. And then over 5 to go up 1 1/5, I suppose, from there. So those are a couple points. But furthermore, it looks like my A value, if I'm going 6 to go down 1, my A value must be negative 6. Negative 6 divided by 6 is negative 1. A is negative 6. So I can figure out more points like that just by knowing the A value there. So negative 6 over 1 is negative 6. 6 down from there. 6 divided by 2 is 3. 6 divided by 3 is 2. We can move forward. 6 divided by 12 is 1/2. 6 divided by 1/2 is 12. 12 down from 1 is negative 11. I mean, guys, I'm getting points really quickly. If I haven't convinced you yet, I don't know if I will. If you're like, I'm convinced, I just can't do it for myself, I don't know. You can keep following along, see if it makes sense over time. Try and pause it and do it on your own on some of them, and then go, like that's the point of this video, right? It's not a live stream where you have to catch up to what I say. You can try some on your own and then compare it and see how you do. That's a part of it. Or you can use a table. No one's stopping you. I like getting those critical points first, though, so I'm not struggling as to what values I can find. Even when my y-intercept was a fraction, it was easy to get. It's not like I had to plug in, 2, and I go, 2 minus 1 is 1, and 2 plus 5 is 7. I have to compute things. No, when I plug in 0, these just go away. It's just really easy. Just boom, there's my y-intercept. I'm not calculating anything, even though it's a fraction. All right, number 27. Now, these ones can get weird, and this is where, admittedly, even I'm going to have a little bit of trouble with recognizing that A value and such and such. Maybe it's not going to be great. We'll do what we can. We'll make do with what we have. So x plus 6 over 4x minus 8. Honestly, I didn't anticipate these, but they'll show up. These are going to be troublesome no matter what you do. Table, no table, whatever. We have a fraction horizontal asymptote. If you can't tell yet, we're about to get there. The vertical asymptote, keep in mind, this is where 4x minus 8 equals 0, 4x equals 8, x equals 2. We have a vertical asymptote at x. Oh, I didn't mention domain and range here, by the way. Give me 1 second. Domain, x can't equal negative 5. Range, y can't equal 1. Okay, sorry about that. Okay, so x equals 2 is the vertical asymptote. Horizontal asymptote is where you are dividing 1 by 4, 1 over 4. 1 divided by 4 is 1/4. And there that one is. So unless I'm changing my scales, which I don't plan on doing so, y equals 1/4 is probably looking something near that. Maybe I can space it out a little more like that. X equals 2 clearly is here. So not fun, right? Not fun. Let's still get some intercepts out from this and figure out the nature of this graph all the same. Can I get that point, please? I'm going to shift this one to the left. There we go. All right. X-intercept, you set the top equal to 0. If x plus 6 equals 0, then you get x is negative 6. Y-intercept, you set x equal to 0, and you get 6 over negative 8, which is negative 3/4. So those are 2 additional points I can get. Negative 6, 0, and 0, negative 3/4. Now, neither of which really got me anything with respect to an A value. Not yet, at least. We can, well, actually, no. I actually take it back. This one did. You know what negative 3/4 is? It's 1 away from 1/4. The only problem is everything's going to be at 1/4. So what am I dividing by negative 2 to get negative 1? I divide 2 by negative 2 to get negative 1. Therefore, my a value is 2. 2 divided by negative 2 is negative 1, dot, dot, dot. That's what we're doing there. So my a value is 2. I can get the rest of the points from this. I can also do reflective points, but how far did I go away? 8 away to go a quarter down. So I can go 8 away to go a quarter up. That's at 1/2 like that. I will confirm that's what we hit, by the way. For the y-intercept, you will see that one for sure. 2 divided by 1 is 2. Now, 2 up from a quarter, this is where the problem sits, is 2 1/4. 2 divided by 2 is 1, so that's 1 1/4 there. And that one is the reflective piece of this one. 2 right, 1 up, 2 left, 1 down, and those points kind of work that way. 2 divided by 4 is a half. Halfway up from a quarter is 3/4. And 2 over 8 is 1/4, and 1/4 up from a quarter is a half. So that's where that one hits. 2 divided by a half, this is going to be hard to really hit, is 4 up. That's 4 1/4. And 2 divided by a quarter is 8, so 8 1/4. Oh boy. No matter what we do, guys, we're going to have some weird numbers. I'm sure there's one that hits an integer somewhere, and it's not worth seeking. Just do what you can, or draw the curve, right? I might as well point to it right now, guys. If you want to see more complicated rational functions, actually, you know what? I'm going to point to it later. I think we're going to hit more complicated ones later. But you want to see more complicated rational functions, you're going to see I'm not going to plot as many points as this one, but I am getting what I can now. 2 divided by 1 is 2. It's negative 1 3/4. 2 divided by 2 is 1. We have that. 2 divided by 4 is a half. So negative 1/4 there. And 2 divided by 8 is a quarter. That's where that one comes from. 2 divided by a half is 4. 1, 2, 3, 4. And 2 divided by 1/4 is 8. 5, 6, 7, 8. A quarter away. Okay. A lot of points to get. Got them. We draw the curve. Let's still do domain and range after. I don't want to forget it. Okay, we got that one. We got that one. All right. Crazy graph. Okay. Domain. X can't equal 2. Range. Y can't equal 1/4. All right. No matter what we did for that graph, it would be crazy. Number 28. And after 28, there's still 30 problems to go. Imagine that. H of x equals H of Ultron. 8x plus 3 over 2x minus 6. All right. Let me work with the bigger graph axes that I've been using. Too big. Too big. Okay. Vertical asymptote. 2x minus 6. If that equals 0, add 6 divided by 2. That would be x equals 3, which means x can't equal 3, right? That's our domain. X can't equal 3. Horizontal asymptote, you divide 8 by 2 with these x's being the same, and you get 4. So we got 3 and 4, a little farther out than we've had. X equals 3, y equals 4. Okay. Intercepts. Y-intercept, you set x equal to 0, you get 3 over negative 6, which is negative 1/2. X-intercept, you set 8x plus 3 equals 0. Oh, this one's not good. You subtract 3 and divide by 8, you get x equals negative 3/8. So these ones ain't quite as fanciful. So we might have to do a little bit more work when it comes to determining the a value. Won't be terrible, but we'll still get it. Negative 3/8. Yeah, that's why. Negative 3/8 is less than a half, so probably right there. Not great points to deal with in general. Let's do the thing where, excuse me, I'm going to substitute 1 away from here, like 4 for x or 3 for x. Doesn't really matter. I'm going to substitute, say, 4 for x. Well, you know what? That might be too big a number. Let's substitute 3 for x. I'm substitute 3 for x, one table value and determine our a. So when we're plugging in negative 1, what is our a divided by negative 1? And we get 24 plus 3 over, I'm sorry, not 3, 2, 2. I'm sorry. I don't know why I was saying 3. Plugging 2 for x. 16 plus 3 over, ooh, that's a hideous number. 4 minus 6 is negative 2. That's still not good. Oh, no matter what we do, guys, we're going to have some weird numbers. This is just fraction ahoy. Even plugging in negative 1. Our a value, in essence, is negative 9.5. I mean, what do we do with that? Negative 9.5? Even when I substitute it in 2. These are the right numbers, right? 16 plus 3 is 19. 4 minus 6 is negative 2. Yeah. So I get 9.5 down. 9.5. And I can also go 9.5 up. This is where I said it would fall off the graph, and it does. Because I plug in 4, I'd get not positive 9. Oh, I'm sorry. It's not negative 9.5 down from the asymptote. It's negative 9.5 down as a y value. See, that's the one problem. I just confused myself there. So there's negative 9.5 like that. That's really far down, which means it goes really high up. This is one of the graphs where I'm less concerned about like doing a lot with it, especially because I won't be able to fit a lot here. I'll try and reflect these points, and I'm going to try and get another point over here. If I went down technically not just 9.5 but 13.5, I could also go 13.5 this way just to go 1 down. 13 is here, 13.5 is like there, 1 down, that's another point. So this has incredible distancing to it with not getting a bunch of other points along the way. The only true points I'm really going to get from this other side, if y'all don't mind, are the reflections of the x and y intercepts. So the x-intercept is 3 3/8 over to go 4 down. So let's go 3 3/8 over to go 4 up, like that. And the y-intercept is 3 over to go 4.5 down. So let's go 3 over to go 4.5 up, like that. And really not many other points that could be fitting on that one anyway. So I don't know, the graph is doing something like that as it's going to approach like 13.5 up from there and do that kind of stuff. So there is our graph on number 28. Not a fanciful one, but it is right. Domain, x can't equal 3, range, y can't equal 4. You're challenging me, rational functions. Number 29. I'll tell you what, these intercepts won't be glorious. So they're, listen, not clean. Not clean. Number 29, we got f of x equals negative 5x plus 2 over 4x plus 5. And guys, I'm telling you right now, I'm not, my tableless method is still faster than method with a table, especially when I'm only trying to get clean numbers out as a result. It's not like using a table will go faster. Okay, so critical points and all that we're still trying to find. Vertical asymptote, 4x plus 5 equals 0 is our scenario for that. We subtract 5 and divide by 4. We get x equals negative 5/4. So already, this is going to be my least favorite graph. Negative 1.25, x equals negative 1.25. Already we're kind of in deep doo-doo with that. Horizontal asymptote, not looking much better here. This is where, well, it's negative 5/4 as well. You divide negative 5 by 4. And we get that, guys. So a couple negative 5/4 along the way. Negative 1.25, negative 1.25, if you will, on that one. And we got that. So asymptotes. X-intercept, we set negative 5x plus 2 equal to 0. And subtract 2 and divide by negative 5, you get x equals 2/5. So there's our x-intercept. So at 2/5 comma 0, 0.4, like that, is a point. Oh, there's nothing here that's going to be fun with what we do. Unless 2/5 is a certain, no. Y-intercept is also 2/5. Okay, so there's symmetry for sure. It's just not one for which we can do a lot with. So y-intercept is 2/5. When you set x equal to 0, you get 2 over 5. So 2/5 up like that is a 0.4 in that direction as well. Listen, there aren't any valid integer values that we're going to be trying to find anyway. And even if we did, these are at fractions to begin with. So how do I really work this thing out and make it good? Couldn't tell you, man. This is not one that we tend to lean into very often. I don't know. It's one of these times where maybe using a table is what you do. But listen, look, by using a table, they mean plug in values. Look, let's plug in some values. What if I substitute, I don't know, 5 into here? Okay, well, what's f of 5? I'm going to do this mentally. Negative 25 plus 2 is negative 23 over 20 plus 5 is 25. You see where it's not necessarily, I'm not getting much from that. So plug in 5, you get negative 23 25ths. I guess it's a point. I'm not going to lie, it's a point on there, but what did I get out of that, right? Let's substitute negative 4. F of negative 4 is 20 plus 2, so 22 over negative 16 plus 5, negative 11. Hey, that's actually an integer. That was weird. So that's negative 2. It's not a certain distance away from anything that means I can reflect a point very well. I got negative 2. Okay, there's a point. But you're plugging things in to get values out, right? Eventually, there's just an approach. And that's honestly when graphs get more complicated than this. My only care and concern is where are the asymptotes, what do they approach, and where are the branches drawn? I'm going to use their word. Where are the branches drawn? In what quadrants? In what areas on this thing? And that's where I'm going to draw this one. So when I can't get more specific, I won't dare to try to. And really, it was built off these asymptotes being weird fractions and nothing really being built off of from that. So let's seek greater fortunes on number 30. I'm not positive on that. If it's anything like any other problems, 30 might just be another version of 29. Looks like it might be better. We'll see. G of x equals 6x minus 1 over 3x minus 1. So some parts better, some parts not really. The y values look like they'll be okay. X values, I don't think so. Oh, I didn't state domain and range off the last one. I'm sorry. So we have domain. X can't equal negative 5/4 and range. Y can't equal negative 5/4. All right, so let's go back to number 30. On number 30, we have a vertical asymptote at add 1 divided by 3, x equals 1/3. Again, weirdo fraction. Horizontal asymptote, 6 divided by 3 is what happens here. That's y equals 2. So that one's fine. The other one, not so much. So do what we can. X equals 1/3. Yeah, I can't do much better, really. X-intercept, y-intercept. Let's start with the y-intercept. That one's easier. Set these to 0. You get negative 1 over negative 1, which is 1. X-intercept, you add 1 divided by 6. You set the numerator equal to 0, and you get 1/6. So 1/6 is halfway between 1/3 and 0, so it's right there. Y-intercept of 1 is right here. Now, the 1... this might still be able to answer something for me. If I go 1/3 away, I'm going 1 down, right? If a divided by 1/3 is negative 1, then a is negative 1/3. If that helps regarding stretch factor stuff. So it just goes to show just how small this will be anyway. Divide by 1/3, you get 1. That means you divide by 1, you get 1/3. And remember, it's 1 away from 1/3. So you divide by 1, you get 1/3 like that. So there aren't really many great points I can get here. I divide by 1/3 this way. That's 2/3 over. I get 1. Divide by 1, you get 1/3 up from there. So nothing really great. This will be a condensed graph no matter what you do. So not much I can do on this one, guys. I'm going to go ahead and leave it as that based off the points that we did find. That a value there being so small, there's not much we're going to be able to do with this graph. Boo hiss. It happens. It's not like we're going to cry about it. There we go. So, domain. X can't equal 1/3. Range. Y can't equal 2. Now, you might sit here going like, why do you identify the vertical and horizontal asymptotes just to write domain and range as what it can't equal later? Why don't you just start with this? Good point. Fair point. Later, someday, they might ask you to identify these as they are, especially in pre-calc and such. And I think it's just something I habitually do. I don't often stretch for domain. I don't often reach for domain and range like that. That comes after the fact when I do my graphs generally. Number 31. I think, I haven't done these in a while. My last time I've done a video on rational functions was over a couple years ago. So negative 5x over negative 2x minus 3. Interesting where there's no other constant here, but if we did have one, it would be a plus 0. Shane? You understand? So that's important when we start talking, you know, y-intercept. Let's move all this over, though. That being said. All right, but let's start with our vertical and horizontal asymptotes. So vertical asymptote, add 3 divided by -2, you get -3/2. So we're back to some weird stuff. -5 over -2 is +5/2 for y. At least they're halves and not like quarters, but even still, not my favorite. -3/2 is -1.5 for the vertical. Let's try and get that a little better. The horizontal is +5/2. That's 2.5. So like that. Okay. From there, we will x-intercept, y-intercept. So the y-intercept is easy this time. It's actually 0. Y-intercept is 0 because we're dividing 0 by 3. That's what happens when you substitute 0 for x on top and bottom. So we get, and that means the x-intercept is 0 as well, right? I mean, think about it. If you set -5x equal to 0, you get x equals 0. So the x-intercept is 0 as well. That's more bad than good for me. That means there's only one critical point we get out of that, not 2 unique ones. I will try and reflect it, though. I'm going 1.5 away to go 2.5 down, so I can go 1.5 away here to go 2.5 up. That means there's another point like that. That doesn't help identify my A value, and even if I do identify it by plugging, listen, I'll get it. That's fine. But I have to plug in a decimal to make it work. So I don't know if this is going to pan out in a way that helps us. So let's plug in, say, 1 away is at -1/2. Actually, let's just do it like this. We plugged in, we divided A by 1.5, and we got -2.5. I guess we don't have to do it that way. So A value multiplied by 1.5, I don't know what that is. It's not clean. So this won't help us. 1.5 times 2.5 is 3.75. So hey guys, that's our A value. It's negative 3.75. So 1 away is 3.75 down. 1/2, 1.5, 2.5, 3.5, 3.75 is like that. There ain't nothing good about what we're doing from these numbers here. So this is another set where plugging in numbers, you're just going to get decimals out. I'll do one more set for you by plugging them in, just to satisfy it. I'll even go 3.75 over to go 1 down. But, you know, it's these kinds that get a little just funky, right? 1/2, 1.5, 2.5, 3.5, 3.75 is like that, right? Yeah, let's go 3.75 over. 1/2, 1.5, 2.5, 3.5, 3.75 over to go 1 up. No, to go 1 down, excuse me. Go 1 down. And 1/2, 1.5, 2.5, 3.5, 3.75 over to go 1 up. All right, let's plug in 1. -5 over... Oh, -5 is -1. All right. Or is +1. So then I guess we can plug in this one to go, I guess the same amount, I guess it's going to go here. You plug in -4, you get 20 over 5, which is 4. And that's where that point is. Okay, so we got a few points out of that. Enough to make my curve, know my destinations, things like that, my approach. All right, domain. Yes, sir. X can't equal -3/2. Y, range, Y can't equal 5/2. All right, one more on this set before we do our long division sets, and hopefully those will be clean enough numbers each time we have them. I can't guarantee it at all. Number 32. We have Y equals -2x plus 3 over -x plus 10. When it comes to asymptotes, we're in good shape for integers. I've been waiting for those again. It's been a while. It's been a minute. Vertical asymptote, add x to both sides, get x equals 10. The only problem with that is it's a little stretched far out. I can't really get any points on the other side of it. Horizontal asymptote, you divide -2 by -1 and you get +2. So horizontal asymptote, pretty good, pretty fine. X equals 10, a little far out. I guess this is why they scale by 2 sometimes. Do I plan on doing it? No. I already have. Look, I got what I came here for, which is features. Y-intercept, these aren't good numbers, but y-intercept, set x equal to 0, you get 3/10. X-intercept, you set the numerator equal to 0. You add 2x and divide by 2, you get x equals 3/2. So 3/10 and 3/2. So 3/10 comma 0, or 0 comma 3/10 I should say, and 3/2 comma 0. Probably looking like that. Look, I'm not going to fit other points on this other side anyway. If I were to get something out from that, how far away? Oh, geez. Okay, let's plug in a number. Let's plug in 9. This is going to be a tall graph. It's not going to be able to fit points, but let's plug in 9. Negative 18 plus 3 is negative 15 over negative 9 plus 10 is 1. So negative 15 over 1 is negative 15. And that's not negative 15 down from the asymptote. That's negative 15 as a y value. It's all the way down there. Really won't fit it in any sort of good way. That means it's 17 away from there. That means our a value is 17. If you want an answer to that, our a value is 17. 17 can't divide by any good numbers other than, well, 17. 17 over 17 is 1. If you want me to kind of prove this one, I go to negative 7. I should be able to substitute negative 7 for x, and I should get positive 1 for y. Take a look. Negative 2 times negative 7 is 14, plus 3 is 17. Opposite of negative 7 is 7, plus 10 is 17. 17 over 17 is 1. There's that point. That kind of further proves my a value is 17. So, not much I can get from that otherwise, though. What? I could divide it by 2 and get 8.5. Divide it by negative 2 and get negative 8.5 from there. All right, there's a point. Divided by negative 8.5, I get negative 2, but we already have that point. That's right there. Okay, so anyway, we have some points there. The other side, I'm not really going to fit anything appreciable, so I'll just kind of draw a fake curve. Just a curve that goes on that side. It's good enough to just note that it is on that side of the graph. And you might wonder how I know it's on that side of the graph, besides the fact that every graph has looked like that so far. There are some graphs that won't, but as long as they're linear, they will. What you have to keep in mind is there's only one x-intercept here. Okay, that's really all I can fit. What you have to keep in mind is there's only one x-intercept here. If the graph went on this side like this, it would hit another x-axis somewhere, and it doesn't. It doesn't have another x-intercept, so that's all we have. All right, your domain. Domain, x can't equal 10. Range, y can't equal 2. Things were looking good before a became 17. Okay. All right, let's move forward. Numbers 33 to 40, we are now going to use long division. Well, you can use synthetic division as well. And I actually probably intend to use synthetic division more often, but trade-off. Let's do trade-offs. Long division one, synthetic division on the other. We can do division to get back in that graphing form that we were using before, where the a value exists, things like that. We can still do x, y, and so you can do whatever you want on these things, but it's just saying, let's do it a different way. Let's do it a different way. So before we actually do the graph, even asymptotes, things like that, keep in mind the x plus 1 ain't going to change. I have 5x, let's do this in blue. I have 5x plus 6, I'm dividing by x plus 1. We're basically going to get a rewrite of g of x. X goes into 5x 5 times, you multiply these, you get 5x plus 5, subtract that result, you get 1 as a remainder. It's going to be very quick. Long division ain't that long here. You sure? So your g of x can be a rewrite of, remember, we kind of write the remainder first because that's the a over, and it's still x plus 1, and then plus 5 is your quotient. And this gets us in that form. Now we can graph out of this. So quotient, boom, remainder, boom. Now we can graph as we did before. So I don't even think it's worth writing them. Vertical asymptote, we now know, is x equals negative 1 based off what we've seen in the past. Horizontal asymptote is y equals 5. So getting it in this set. Now, does that agree with what we would have had in the past? Yes, we would have had the negative 1 the same way as before, no change there, and 5 divided by 1 is 5 for horizontal. Cool. So, Mr. Robinson, why would we care to do this instead? Well, now we have an a value. Our a value is 1, and there I can do everything I want to do. 1 divided by 1 is 1, 1 over 2 is a half, 1 over 3 is a third. I can work these that way instead of, doing guesswork and figuring it out, having random x-intercepts that are like fractions, which it would be here. 1 divided by negative 1 is negative 1, and divided by negative 1/2 is 2, negative 2. Divided by negative 1/3 and negative... this would be negative 6/5. Your x-intercept is negative 6/5. You can actually tell by subtracting 6 divided by 5. But you can tell how weird those are. Divide by 2 and 3 and 4. It's weird that it's just a 1. I know, there are fractions still right here. They're not great. Let's wait till we get an a value that's like 4 or 8 or something like that we can get better points off of. But having that a value gets us some points without the mess of what we were doing before by only getting some critical points on x and y intercepts. By the way, y-intercept would have been clean. Y-intercept is 6. Check it out. 6 over 1 is 6. So this is all confirming, this is all confirming what we did before, and it still works itself out in that way. No change. No change, just we represented this differently to get there. Describe the graph of g as a transformation of the graph of f of x equals a over x. Given that the a is still 1 over x for our f of x here, it's basically whatever a we get, okay? So we're just talking about translations. The graph of g is a translation 1 unit left and 5 units up from f. Okay. Number 34. They don't actually ask for domain and range, but there it is. Number 34. This time I'll use synthetic division. For the odds, I'll use long. Evens, I'll use synthetic. G of x equals 7x plus 4 over x minus 3. Prepare the graph. Okay. For this one, hold on. Okay, yeah, I don't mind using synthetic division for any of these. 3 is your root. You have coefficients 7 and 4 for which we divide. Add 7, multiply by 3. Ooh. Add 21, you get 25. That's your remainder. So your equation is g of x equals 25 over x minus 3 plus 7. 7's the quotient, 25 being the remainder. I want to just make sure I did that right. I think I did, but just like, wow, that's going to be significantly different, right? So we have that going there. Does that help us? I don't know. I can divide it by 5, and I think that's the best number I'm going to get out for you guys. So x equals 3 is the vertical asymptote. Y equals 7 is the horizontal asymptote. Yeah, 25 is the a value. 25 over 1 is 25. Forget about it. Heck, even 25 divided by 5, I personally can't fit on my graph very well. You go 5 over 1, 2, 3, 4, 5. You go 1, 2, 3, 4, 5 up like that. Already it's very far removed. You go 5 left, go 5 down. That one fits. So right there. What other ones? I can divide 25 by 2 to get 12.5. So let's go 12.5 down from -7. That's -5.5, I think. It means you can also divide it by 12.5 to get 2. What's 12.5 from here? 10, 11, 12.5, and you get 2. So I'm getting some points out from it. Listen, x and y intercepts, probably not pretty. Y-intercept is y-intercept, let's just do this still. Y-intercept is -4/3, boom. X-intercept would be -4/7. So -4/7, boom. So nothing pretty, but based off what we did before, you can still use those bits if the graph gets so big like this one is. At least it seems to fall in line. It seems to agree with what we had there. This one, I mean, just, it's whatever, right? It's not approaching the asymptote anytime soon. Don't force it to an asymptote if it's not going to. Anyway, what's happening here? The f of x would be 25 over x, so it's just about translations. The graph of g is a translation 3 units right and 7 units up. Whoops. From f. Number 35. G of x equals 2. How long have we gone? Almost 2 hours. G of x equals 2x minus 4 over x minus 5. All right. I shudder in fear over what the quiz question, the chapter test questions will be like, because those are the ones that they tend to stay tricky on. They're asking a lot of you. Let's go back to long division. 2x minus 4 divided by x minus 5 and get a rewrite of our g of x equation. X goes to 2x 2 times. We multiply these. -5 times 2 is -10. Subtract your result. -4 minus -10 is -4 plus 10, which is 6. 6 being your remainder. Your function g of x can be rewritten as the remainder over x minus 5 plus the quotient of 2. Fair. Good. I like this one. So this one, x equals 5. y equals 2 are our values there. We can use 6. 6 divided by 1 is 6. 6 up from 2 is 8. 6 divided by 2 is 3. 6 divided by 3 is 2. 6 divided by 4 is 1.5. I just plot it just because I'm running out of room. 5 and 6. You go 6 over from 5. That's at 11. You go 1 up right there. All right. 6 over negative 1 is negative 6. 6 down from there is there. 6 over 2 is 3. Over 3 is 2. Hey, that is the x-intercept, just so you know. We'll talk about the y-intercept in a second. 6 over 6 is 1. 6 over 12, which I could fit, is 1/2. And 6 over 1/2 is 12, which I could actually fit down there. Now, 6 over 5 is literally 6/5, so that'd be right there. So our y value is 6/5 down from 2, which is 4/5. Does that make sense? Yes. Negative 4 over negative 5 is positive 4/5. The x-intercept, add 4 divided by 2. From there, x equals 2. Yes, that makes sense. So we are agreeing in our values with intercepts without actually needing to do those points, yet we got more by doing the division, which is just fantastic. Grandissimo. Was that all I wanted to bring up? I think so. I don't know if there's anything else I wanted to mention. But yeah, man, I can get intercepts either using the form of the equation, the original form, or just by saying how far do I have to go over and then, divide 6 from it. So your, not domain and range, translations, 5 right, 2 up. As f of x would have the 6 as well, apparently. Okay, number 36. Synthetic division returns. Hope you don't mind. We got ourselves a g of x partner, 4x minus 11 over x minus 2. Okay. So this one, using synthetic division, 2 is your root. 4 and negative 11 are the coefficients. 4 comes down, times 2 is 8, and that's negative 3 as your remainder. So our equation can be rewritten as, in a over x minus h plus k form, a is negative 3 divided by the x minus 2, and then 4 is your quotient plus 4. Also a fine equation for what we're doing. As long as things aren't fractions and stuff, this thing should be just fine. So 2 right, 4 up. Looks like we're going right and up quite often here. Negative 3 is our a value, so we are going to be going right and down to plot them. 3 divided by 1, 3 divided by 3, heck, 3 divided by 2, heck, 3 divided by 1.5, now that we're starting to do some of those. 3 over 6 is a half, 3 over a half is 6, 3 over... yeah, that's it. Oh, that is not 6 down, that is 7 down. Let's try that again. You can tell the x-intercept would be wonky, right? It would actually be 11/4, 2 3/4. I'm not bothering plotting it, but that would be the randomness of that one. 3 over negative 1, 3 over negative 3, heck, 3 over negative 2, heck, 3 over negative 1.5. 3 over 6, 4, 5, 6 is 1/2, and 3 over half is 6, 6 up from 4 is 10. Great. Awesome. Oh, what am I doing? I'm going from, give me 1 second. Oh my goodness, I'd never do that. I was going from the y-axis. I need to go from the vertical asymptote. Let's shift this all over like that. There we go, my bad. I was like, I'm not approaching the asymptote from this. This is way, way wrong. All right, let's do that again. Sorry. I was going to say, why is there no y-intercept? Speaking of which, this y-intercept looks like it's at 5.5. Should it be at 5.5? Substitute 0 for x in your original equation. What do you get? Negative 11 over negative 2 is positive 11 over 2, or 5.5. Yes, 5.5 is it. The x-intercept's a random one. Not going to bother with it. We're all good. Now, unless they ask us for those features, the graph of G is a translation 2 units right and 4 units up from F. All right. Halfway done with those. I don't really know if I can get much faster. They're kind of doing what they're doing. So hopefully we can still deal in that way. Number 37. you get g of x equals x plus 18 over x minus 6. What are we watching? Who is that? The twins? Oh, it's a highlight reel. I thought it was live. We have... What are we trying to get? Oh, let's use long division. X plus 18, x minus 6. X goes into x once. You multiply that there. Boom, via subtraction. 18 minus negative 6 is 18 plus 6, which is 24. Big remainder. And that is our a value. So g of x can be rewritten as 24 over x minus 6. Pretty big. Plus 1. 1 being the quotient. So we got... We're, again, going right and up. That ain't changing anytime soon. Or maybe it is. Maybe it is on the next problem. But going 6 right, 1 up like that. And 24 is our number. Our a value. 24 over 1 is 24. Too big. 24 over 2 is 12. Also too big. We can try and just kind of fit it. Here's like 10, 11, 12. It'd be way up here. We can divide 24 by 3 to get 8. 8 up from 1 is 9. 24. See, numbers start to look good. But we start to run out of room on this other side. 24 over 4 is 6. 3, 4, 5, 6. 24 over 6 is 4. 11, 12, and up 1, 2, 3, 4. We just run out of room. This side will get a little more room, especially going to the left. That's fine, but everything else is kind of eh. 24 over 2 is 12. That'll be a lot closer. 24 over 3 is 8. 24 over 4 is 6. 24 over 6 is 4. 1, 2, 3, 4. 24 over 8 is 3. What are we at? 6, 7, 8 is 1, 2, 3. 24 over 12, that's negative 6, is 2. Yeah, that's a lot more points on that one. I'll use those ones. X-intercept was negative 18. So that's still out of reach. Even if I draw this curve, I shouldn't be going through there because it doesn't hit till x is negative 18. So it takes a while to still get over there, right? That's kind of the idea of what these graphs do. Y-intercept is negative 3. If you double check, go to the top, set x equal to 0, you get 18 over negative 6. That is negative 3. So this graph agrees. This graph agrees. I ain't doing nothing wrong. I ain't done messed up yet. All right. But I graph what I can. Hey, our f of x equation is 24 over x. This is just a translation. The graph of g is a translation. 6 units right and 1 unit up from f. All right. There we go. Number 38. G of x equals x plus 2 over x minus 8. We'll use synthetic on this one. Because why not? Your root is 8. Your coefficients on top are 1 and 2. Through synthetic division, we get 10 as the remainder. That one's not bad. Problem is the 8 here. 8 is the part of the vertical asymptote, right? So our equation is 10 over x minus 8. What's happening? It's kind of glitching. 10 over x minus 8 and then plus 1. Plus 1. So 8 and 1. Still going right and up. Right on up. 10. Whew. Can't fit much on this right side here. 10 over 1 is 10. 10 up from 1 is 11. All right. 10 over 2 is 5. 10 over 5 is 2. I can't fit 5 over. That's it. Let's go to this other side, though. 10 over negative 1 is negative 10. So 10 down from 1 is negative 9. 10 over 2 is negative 5. Down from there is negative 4. 10 over 5 1, 2, 3, 4, 5, is negative 2. 10 over 10 is negative 1. And that is the x-intercept. That makes sense. X plus 2 equals 0. X is negative 2. Y-intercept is negative 1. Wait. Oh, it's negative 1/4. Yeah, so negative 1/4 down from here. So that's the y-intercept. Boom, if you want to plot that. 10 over 20 and 1/2. I can't really fit it somewhere over there. Okay, so the approach thing is still good though. So we're going to get a nice long venture here. Yeah, I like using both sets of features there. Using the division to get that A value is really nice. And then just confirming intercepts when we can, or seeking intercepts via the original equation, gets you more information than not. So I really do like that about it. I'm taking advantage of it, making use of all of it. So instead of 10 over x, we have 10 over x minus 8 plus 1. So the graph of G is a translation, 8 units right and 1 unit up from F. All right. The last two problems, at least we're destined to go left instead of right. You can tell because, well, actually the first one we went left. Did I graph it left? I want to make sure I did because okay, we did. That was the last time we went left. Now we're destined to go left once again. Are we going to go down at some point? We'll figure it out. So number 39. We have g of x equals 7x minus 20. I'll tell you what this y-intercept would be. The x and y-intercepts of these would be a nightmare. Let's see what happens on the graphs in general, just through our division. Let's paste this graph in. Man, this is a longer video. I didn't know how long to anticipate. We're at 2 hours. And I tell you what, my stomach is making the rumblies that only hands would satisfy. If you don't know the reference, look up llamas with hats. Kind of weird. It's kind of weird, but it's funny. All right, x goes into 7x 7 times. Multiply. If you've seen Charlie the Unicorn, it's the same guy that does. Wow. What's 7 times 13? Hold on a second. 93? No, wait, what? 91. Am I right? 91? Plus 91. Wow. Whoa. What? This is our A value, guys. When we subtract this, we get negative 111. All right, things were looking good to me for a sec. Oh, you know what? This is already bad to begin with, the plus 13. I'm going to have to change some sort of scale, clearly. I'm going to have to change some sort of scale. So we do have, g of x. Now they just decided to become mean. You know, when I vowed and said I'd do every problem in a solution guide video, I didn't really mean every problem to actually do this. All right, negative 111 over x plus 13, and then 7 is the quotient, so plus 7 like that. All right, clearly we got to make some changes here. I might even go as far as going by tens. Negative 111 is this thing. So let's call this 50 and 100, negative 50 and negative 100, etc. We're going to go by tens. I don't intend to change scales a lot, but this is one of them. Now, this still isn't going to be fun because I have 7 and negative 13 as my asymptotes. So negative 13 is, negative 1 3/10 over this way now. And that's kind of as close as I think I can get there. What looks better? That or that? I'm really debating on which of these two things looks better. Let's just enlarge this a little bit and then we got our answer. There we go. The 7 is 7/10 up. I mean, there's nothing fun about what we're gonna have here. They is what they be. That was good enough. All right. So there are the two pieces of that graph. Man, and then we hit word problems after that. Okay, I'm just taking a look. All right, and then we gotta do some things. So negative 111. I mean, wow. You go 1 over, you'll go 111 down. 111 down. At this point, I might as well use a table. But even then, 111 down from 7 is negative 104. Even then, it's technically off the graph right there. But 1 away at negative 12 is like that. Listen, 111 doesn't divide by much. It doesn't even divide by 11. It's a prime number, right? No, it divides by 3. 111 divided by 3 is 37. So if I go 3 over, I can go 37 down, and that's even a good number. That should be right here. Let's try and confirm that. Plug in negative 10 into here. We get negative 70 minus 20, which is negative 90, and negative 10 plus 13 is 3. Negative 90 over 3 is negative 30, and look, I got that beautiful number right there. That doesn't happen often. So if I go 37, if I go 3 over to go 37 down, I can go 37 over to go 3 down as well, right? 11 divided by 37. What's 37 away from negative 13? It's 24. So to go 3 down from 7 is 4. So 24 is like right there, and 4 is like right there. And that's another fun point. And 111 away to go 1 down. 111 from negative 13. Are you following me even? Is negative 98, or is positive 98, excuse me, to go 1 down right there. Just 1 down to get to 6. All right, as much as I could do with those points. If you want intercepts, you got a y-intercept of negative 20/13. You think that that's anything substantial? That's negative 1 and change on something that's scaled by tens? That don't matter. X-intercept is negative 20 over 7, is positive 20 over 7, which is a little less than 3. You think that point matters? Not really. It's little points like that. So at least we got something. The other side, 1 over to go 111 up. I mean, whatever, something up there. Just huge. And then 3 over. This one isn't as fun this time. 3 over from 13 to go 37 up from 7. So negative 16, comma 44. So negative 1644 is probably about like right there. And same thing for this other one. Going 37. Oh, actually, this one might be good. Going 37 over to go 3 up will be good. So 37 over from 13 is 50. To go 3 up is 10. Okay, that point's good. If you want to confirm that, let's plug in negative 50, see what we get. That's negative 350 minus 20 is negative 370. Whoopsie. Negative 370 over negative 50 plus, over negative 37, which is 10. And that's what we're hitting right there. Boom. So look at that. We're actually getting that point out from it. Very cool. All right, that's all I'm going to plot, guys. It's already weird. Not loving the problem. But I'm confirming everything seems to be exactly as expected. The long division is accurate. The points that I'm going distance-wise from there, it's working. I'm confirming it by plugging the numbers into the original equation. I'm getting those same values out, so it is working out. Even with the intercepts being weird as they are, they seem to go through points that seem to make sense with our graph. So it's going to really curve off like that and do the same thing on the other side. Even though I didn't plot the reflections of the intercepts, they still go off the other side like that. Yeah, wow, I've never anticipated doing something so bizarrely distant like that, but here we are. A over x would be negative 111 over x, so it's still a translation. At least we went left. Yeah, like that matters. All right, number 40. Please be normal. Number 40. Normal-esque. G of x equals 9x minus 3 over x plus 7. See, I thought we were in trouble the first time we had that synthetic division problem. We had an a value of 25. Now we have negative 111. At least it wasn't prime. All right, synthetic division here. Negative 7 is your root. And we got 9 and negative 3 going here. 9 goes down times... Oh, this is going to be big. Negative 63, and here we got negative 66. So there's our remainder that time, which means that is our a value. So g of x equals negative 66. At least it ain't no negative 111, but it might as well be. Negative 66 over x plus 7. And then plus 9. So here's the other problem. And I'm not intent on changing scale. I mean, should I? I might have to change scale. I'll go by... What if I go by 6s? That's weird for the 7. That's weird no matter what I do. I'll go by 6s. Listen, there's nothing beautiful about the graph. They decided on the problem. They built the hole that we have to now make here. So we'll go by 6s. Do what we can. I don't know if I'm going to do this very well when it comes to the overall numbers. You're just going to have to live with it, or hopefully you weren't assigned the problem. I don't know what to say. So 9, at least 9 is, a 6 plus half of 6. So for the horizontal asymptote, it's like 1.5 up right there. That's where 9 would ideally be. The 7 is to the left, None of the 9s went down, did they? Or none of the y's went down, did they? Horizontals. The 7, -7, it's 1 1/6 away from -6. So I got to move it a little bit more over. Kind of probably something like that. Listen, intercepts wouldn't be great regardless of what we do as well. I'll probably just confirm that they hit where they hit. As far as the -66 goes, when I go 1 over, I go 66 down. Now, 1 over is on -6. When I go 66 down from 9, that is, well, it's technically 11 down from here, but that is at 57, which is 9.5 down from there. So it's 5, 6, 7, 8, 9.5. It's all the way down here still. Pretty low, but that is a point. Don't want to lose the fact that that's a point. When I go 1 over, I go 66 down. If I go 3 over, I go 22 down. No, if I go 2 over, I go 33 down. So 2 over, I'm going to try and plot as many points as I can fit. 33 down from 9 is 24. 24 is a good point. So like that. If I go 3 over, I go 22 down. 22 down from 9 is 13, -13. So 3 over, -13. Oh. Oh, I'm sorry. We don't go at 24. We don't go at -24 itself. We got to go 24 down from. Oh, no, yeah, that's right. That's right. I'm saying how far down from 9. Okay, so -13 is just near -12. So 3 over. So -12 is just below it right there. So not really getting much out of that, though. I can go 6 over. 6 over to go 11 down. And 11 down from 9 is -2. So 6 over is just kind of like that. And -2 is just kind of like that. We're not really reaching Providence here. I'll say that much. 11 over. Boy, this isn't really working out very well. 11 over is 6, 12. 11's kind of like that. And then we go 6 down. 6 down from here is just like that. So, yeah, not great. I could continue this path of terribleness, and we'll see what we get. 33, 22, 11. I just went 11 over. Let's go 22 over. 22 over from -7 is +15. 15 is 6, 12.5, like that. And if I'm going that, I'm going 3 down. So 3 down from there is good. That's just going to be at this number here. So at half C's. 33 over from -7, from -7 is 26. 1 to 24, 25, 26 is like that. And then we're going 33 over to go 2 down. Yeah. Is this worth plotting these points? Are you guys getting anything out of this? I don't really know. I mean, I'm getting points. I'm doing table without doing table. You can do table in there all you want. My points are just based off scale. The problem is the scale. These are integers. The problem is the scale. It just gets so big. I'll do one more with the 66. 66 over is 1 down. 66 from -7 is 59. So you're 60, so 59, and then just 1 down right there is like that. So, okay. All right, so we're getting a curve. And that's only 1/2 of it. I mean, I'll do what I do on the other side. I mean, and whatevs. It's just going to be a long problem, so deal with the long problem. All right, on the other side, 1 over is 66 up. 66 up from, I have to keep remembering my numbers, though. 66 up from 9 is 75. That's kind of out of reach, but 66, 72, and it's like 12.5, like that. Just going 1 over. 2 over is 33 up. 33 up from 9 is 42. 42. And 42 is a decent number. The problem is 2 over from 6 is 3, so it's about halfway. So 42 is this guy. 3 over. What are I doing from -7? So 10. 3 over is 22 up. 22 up from 9 is 31. Well, there's 30, so 31 is probably just like that. 6 over is 11 up. 11 up from 9 is 20. So 11 over from 7, though. 11 over from 7 is 18. So that's here. So 18, and what did I say? No, I'm sorry, 6 over. 6 over from 7 is 13. 13, so what is it? 12, 13, and 11 up from 9 is 20. So 12, 18, 20. Now I can go 11 over. 11 over from 7 is 18, which is right here. 6 up from 9 is this guy right there. That one's probably the easiest one to get. 22 over from 7 is 29. It's right next to 30, negative 30. 3 up from there, because 22 over is 3 up. 33 over is 2 up. 33 from 7 is 40. So 36, 40 is there. And then we go 2 up. It's still underneath there. And then 66 over from negative 7 is negative 73. I mean, it's off the map. And then 1 up. It's probably about right there. All right. So getting all those points. This is a lot of work for something where I could just draw a curve. In most cases, I would. But because I had my A value, I felt compelled to do it. Because really the problem is scale. If you have a big enough graph, we have all the integers. I'm fine doing it there. My problem is I'm making fractions out of integers because of my scale. I had nothing better to do, but there it is. All right, the graph of G is translated 7 units left and 9 units up. All right. Okay, guys, that is a lot of those graphs. Let's keep going. Number 41, problem solving. Your school purchases a math software program. The program has an initial cost of $500 plus $20 for each student that uses the program. Estimate how many students must use the program for the average cost per student to fall to $30. Okay, so our Y value is average cost. We are going to divide the total cost that we spend on this thing, which is, this is based off the lecture portion that we saw as well. $20 per student times the number of students plus a $500 upfront cost is how much we spend as an overall. If we divide by the number of students, X is number of students, Y is average cost, then we'll get that set up here. We can use a graphing calculator for this stuff. We'll be fine on that. But it says, estimate how many students must use the program for the average cost per student to fall to $30. I mean, what we can do a lot of things here. We could solve this algebraically. We set Y equal to 30 and we'd solve it. But I think they want to use more graphing calculator stuff. So I'll go to here and we'll do 20x plus 500. Put that in parentheses and divide that by x. I don't know what this will look like, but I just know that first quadrant is all that we care about. So given that, I'm guessing 500 is in the mix. 20x plus 500. I don't know. Do I have to do 500 here and 500? Let's see what we get from this. Oh, no. At least the y's can shrink, right? Because the asymptotically, I don't care about y values that are necessarily so big. Let's check out 100 and see what we're doing. That looks a lot better. Okay, so this went up to 500 for this thing here. I need to figure out for what value. What did I go up to, 100? I need to figure out for what x value gives me a y value close to 30. So there's a trace feature here. And I can trace on this thing and figure out to which part I land at about 30 for y. Somewhere between 29.4 and 30.4. It's around probably 47 to 53 students. Probably around x equals 50 students, right? The trace feature going in between those two. It's probably good enough. I'd say about 50 students there. Now, is that exact? I don't actually know. I'm going to actually plug that in later and figure that out. So about 50 students. That was using the graphing calculator. I do wonder if they actually wanted us to use that or not. If I substitute 30 for y here, here's what happens. Multiply both sides by x, right? That's where we begin. We get 30x equals 20x plus 500. Oh, yeah. Subtract 20x, you get 10x. Divide by 10, you get x equals 50. So, yes, 50 students. It's not even approximately. It is. But they said estimate, so I think they mean use the graphing calculator. But that's the answer. I was just guesstimating. What happens to the average cost as more students use the program? Well, the cost goes down, right? This is how this thing works. You get x goes bigger, you saw y get smaller. Not significantly smaller. There's diminishing returns here. The average cost per student decreases. Actually, I want to talk about something else even more so. I don't think it's just about that. I think that 20 in the fold is working itself out too. Look at this. Your horizontal asymptote would divide 20 by 1 and you'd get 20. If you notice this graph, it's shrinking, sure, but it's shrinking toward a number. You guys notice this? Shrinking toward 20. This actually has a horizontal asymptote at y equals 20. So it decreases, but it doesn't decrease toward 0. Decreases toward 20 over time. That's what that upfront cost thing kind of does to it. Or not the upfront cost. That's what the cost per student kind of does to this thing. Decreases toward $20 as that increases. So that's what I'm seeing out of that. Okay, number 42. After this, I'm going to pause for a moment. That won't matter to you, but you'll see a hitch in the video. Number 42. To join a rock climbing gym, you must pay an initial fee of $100 and a monthly fee of $59. Estimate how many months you must purchase membership for the average cost per month to fall to $69. So we get to do the same things as before, I think, as a whole. The initial fee is $100. The monthly fee is $59. It's times the number of months. We want our monthly average when dividing by X to be $69. Now, given that, we'll go to the graphing thing. I'll confirm it by plugging in our numbers here afterward. But, like solving algebraically. But we're doing 59x plus 100 all over x. Let's see if this window range is good. It's probably fine. I think it slopes out a little too far there. I don't think I need to go that far. Let's check this out. All right, that looks good. All right, $69. Where are we at, given that we're looking at 100? So trace. Let's go to 69. Now, I could also plug in, so it looks like about 60, right? I could, or that's more than 69, but more than 60, and it just keeps going down. So would it be more towards 61? Oh, no. It's still around 60. Okay, I'll just say about 60. It's whatever. What was I going to say? Oh, I could have used the intersect feature instead of the trace feature, or the value feature, and I would have gotten better off. So for part A, I'm going to say, oh, hold on a second. I did this wrong. Let me go back. I'm not figuring out 69 months. I'm figuring out how many months gets me $69. Let's do this again. When is Y 69? So somewhere between 9 and 10. I'm going to guess around 10 months there. So again, maybe that's why they want to use the trace feature, because we're not plugging in a number for X. We're finding a number for X based on Y. So around 10 months. Now, if we do this algebraically, let's see what we get. We substitute 69 here. Let's do a different color here. We multiply both sides by X. Yeah, I think we're going to get this 10 here. We get 69x equals 59x plus 100. Subtract 59x from both sides, you get 10x equals 100. Divided by that, you get x equals 10. So it shows algebraically that that's what we also get. Part B, what happens to the average cost as the number of months you are a member increases? So again, it's the inverse variation thing. It decreases, but so what amount is it decreasing toward? I think this is where you start to see the horizontal asymptote take form again, toward $59. When you look at this graph, that's actually what's happening, right? As x increases, it's getting smaller and smaller, but will it go below 59? You can see it's shrinking, right? It's taking longer to get kind of to where it goes. And after 100 months, you're at least in the $59. Oh, not quite. Getting near that $59 range as I didn't even know I could push this over like this. The trace feature does that. But it slopes off toward $59. And that's the thing. That's the lowest your average can be. I mean, I want you to think about why that is, though, right? We're spending $59 per month already. So your average, without the 100 upfront cost, that would be $59 average already, just per month. How can it be less than $59 ever, no matter how many months? Plus the extra 100, you're always going to be just above $59 on average because the 100 that existed upfront. So that totally makes sense to me, and I hope it does make sense to you as well. Let's see, what do I say? The average cost decreases toward $59 after unlimited months. All right, quick pause. Okay, I'm back. And, I just got to thinking that, speaking of averages, how blessed I was with section 6.1 to be such a short section that I got it done, I think, in under an hour, right? Around 50 minutes. And this one's just averaging itself out. It says a lot of averages means this next section had to be super long in comparison because we still have, 16 problems to go. All right, number 43, using structure. What is the vertical asymptote of the graph? Oh, this is a quick one. What is the vertical asymptote of the graph of the function y equals 2 over x plus 4 plus 7? The vertical asymptote is where you can't equal 0 with your domain. Excuse me, where you can't divide by 0. Given your domain, x can't equal -4, therefore x equals -4 is your vertical asymptote. So let me just kind of write, I'm not going to draw it. Let me just write that out. Vertical asymptote, x equals -4. I think part of that, so B, I think part of that is they haven't had us identify asymptotes. They've had us identify domains and translations. This is the first time that they spoke on asymptotes. I've been speaking on it the whole time, so it seemed like an easy problem. But I think that's where you start to have the conversation. Good thing I've been having conversations on intercepts before. So number 44, what are the x-intercepts of the graph of the function here? Now this one is slightly different. This is one of those more complicated graphs, even than the ones we've been doing, where I would definitely feature things like intercepts and such. It says x-intercept or x-intercepts. So the tricky part about this one is we are trying to, oh, actually, I take it back. I was thinking of asymptotes. There are two asymptotes here. I'm just going to point it out because we might have to deal with these later. Who knows? But vertical asymptotes are at x equals 1 and x equals -1. If you think about that, add 1, take the square to both sides. There are two of them, and those are crazy ones. That's not what we're answering, though, by the way. It's this part. X-intercept is x minus 5 equals 0, x equals 5. This is the x-intercept. So x-intercept is at 5, 0. Oh, B. I didn't notice it was multiple choice. So option B here. The one, oh, by the way, the 1 and -1 right here, those are your vertical asymptotes. Those are answers to something for the graph, but not this thing, x-intercept. Your y-intercept is also actually 5. You divide -5 by -1 when substituting 0 for x. You also get a y-intercept there of 5. Different reasons, etc. But we're there. Number 45. When it says using tools, I assume it's a graphing calculator, especially given the equation we're looking at. Probably a graphing calculator. The time t in seconds it takes for sound to travel 1 kilometer can be modeled by this. I got a lowercase t and capital T. Make sure that you are using both the same here as well. Where capital T is the air temperature in degrees Celsius. All right, that's it. Number 46. No, just kidding. We got parts A and B. You are 1 kilometer from a lightning strike. The time in seconds, 1 kilometer from. You hear the thunder 2.9 seconds later. Use a graph to find the approximate air temperature. I don't think the distance. Oh, travel 1 kilometer. I see what they're saying. I would say I don't think the distance matters, but that's what they're talking about. The 1 kilometer there based off time. All right, so graphing calculator. I'm going to at least do the equation. I got 1,000 divided by 0.6. This is an x. Okay, what they want is, I have to change window range. Just give me a second. I don't know what's going to look good. Let's see what this looks like now. Very small, right? Because this is time in seconds. So I need my time to be, well, quite small here. Let's look at 5 and see what's going on. Even then. But, oh, there's a shift. Temperature can be negative. See what this looks like. I don't know what this graph looks like. That's too flat. Okay, so, okay, what do they want? What do they want? Let's stop playing with that. You hear the thunder 2.9 seconds later. Use a graph to find the approximate air temperature. So I have to figure out when I get 2.9 on this graph here. So I think I do got to zoom this out for x's. You can't be negative 100 degrees Celsius, I don't think. But there's somewhere we got to find out where this thing is curving. So 2.9 with the old trace feature. Let's find out when y is about 2.9. Probably around 23. It's really close right there. Probably around 23. Something we could solve algebraically, right? Maybe I should zoom in on that one. Let's zoom in there. Because they're talking about estimations and use the use a graphing calculator, use that kind of stuff. So if I trace, now I can get closer to 2.9. There we go. Yeah, I'd say we're around 23, guys. Around 23. What is it? 23 degrees Celsius. So 2.9 seconds. So for A, I'm going to say around 23 degrees Celsius. I'm not going to solve that algebraically. That's looking pretty good with regard to those numbers, especially after I zoomed in. Part B, find the average rate of change in the time it takes sound to travel 1 kilometer as the air temperature increases from 0 degrees Celsius to 10 degrees Celsius. Okay, this is one of those things where you're basically finding the slope. I want to find out what T of 0 is, and you substitute 0 for capital T. So that'll be 1,000 over 331. I'm just going to leave it like that for now. And T of 10 is 1,000 over 0.6 plus 331, so over 337. Let's just leave them like those. I don't think they reduce as fractions anyway, so we have that. So what we're doing is a y2 minus y1 over x2 minus x1. The slope, the average rate of change here is T of 10 minus T of 0 over 10 minus 0. So we're going to do 1,000 over 337 minus 1,000 over 331. Not common denominators. We'll just use the calculator. All divided by 10. Should be small. You can see it's a very flat rate, so it should be a very, very small slope as an overall. How many seconds per degree, is that it? How many seconds per degree we change, I think we say. So we'll do 1,000 over 337 minus 1,000 over 331. And it should be negative divided by 10. So negative 0.00537. Was there 5.3? I'll put 538. It's quite a bit. Seconds per degree Celsius. So every change, every 1 degree Celsius we increase, this is how much faster we hear, this is how much sooner we hear the thunder from those lightning strikes, right? For every 1 degree Celsius change. So not significant in any sort of way. They're just giving you scientific information, and I'm inclined to believe it. All right, number 46, modeling with mathematics. A business is studying the cost to remove a pollutant from the ground at its site. I'll pretend like I know what they're talking about. The function y equals 15x over 1.1 minus x estimates the cost y in thousands of dollars to remove x% expressed as a decimal of the pollutant. I'm gonna have to reread that later. Let's see what part A asks. Describe the function, graph the function, describe a reasonable domain and range. All right, I don't know if they want us to use a calculator or not. This I don't know, are the numbers bad? The x-intercept's 1 point, or the vertical asymptote's 1.1. Maybe I should just use the graphing calculator. But what we're going to do negative numbers matter? The function represents the estimated cost to remove x%. So I guess x is the decimal equivalent. So 0.2 would be 20%. Actually, we're going to do 0.2. 0.2 is 20%, things like that. And then we'll know how much costs in thousands of dollars. I'm going to use the graphing calculator. I think we got to plug in some numbers there anyway to make this thing work. I normally silence my phone before these. I got a scam caller. I hope that didn't just demonetize me by playing Jimmy Eat World Sweetness. Hold on, I'm going to silent. I'm between whether I use a graphing calculator or not. This one said using tools. This one does not. I'm wondering, maybe I don't use a graphing calculator. So let's try and not use a graphing calculator. Sorry for me going back and forth between that. All right, so we are going to graph. Now, the vertical asymptote is no fun. This is 1.1. That's the value of x. It makes y 0. The horizontal asymptote is fine, but it's small. 15 over negative 1. Remember, it's about this number, not this number. So it's negative 15. You know what? I'm using the graphing calculator. With respect to what we doing, Graphing calculator makes most sense. So 15x, I don't know if that's what they wanted, but you can't give me numbers like that and make me change scale and use decimals at the same time and have something that'll work out fine. That being said, I have to change the window of this one as well. This thing goes up to 15 or down to negative 15 and things like that. Look at that window. Let's just make it big. Let's go from, now X don't have to go big, right? X's should actually stay pretty small. Let's go -5 to 5, while Y's can go from like -100 to 100. I think that this can actually change like this quite significantly. Now, what you'll see here is they won't draw, well, they kind of drew an asymptote. That wasn't really their intention there. That's a look of the graph. That normally wouldn't be drawn there. I wonder why that's there. That's kind of weird. But I guess that's the graph there. All right, well, I'll copy and paste it at least. So, sorry, this isn't going to be the best form of a problem. We'll do what we can. What we do have, though, with regard to asymptotes are what I stated. We have a vertical asymptote here that is at x equals 1.1. I'm going to change the color and thickness and stuff. Give me a second. Boop, boop, boop. Right there. And then a horizontal asymptote at y equals -15. That's how this scale is working. It's quite a strange scale, but it is what it is. So there are our asymptotes. And then they said, describe a reasonable domain and range. Here's the thing. X is a percentage removal. It's expressed as a decimal. We can remove as little as 0%. To me, you can remove as little as 0% or as much as 100%. A business is studying the cost to remove a pollutant from the ground at its site. The function S models the estimated cost in $1,000 to remove X%. I think you can remove anywhere between 0 and 100%. So I believe my domain is X being between 0 and 1. I think it can include it. I don't see a reason why you can't remove 0% of what you have. It's not like I divide by 0 there. But the fact of the matter is when I substitute 0 in for X, I do get 0 for Y. 15 times 0 is 0. Over 1.1 minus 0 is 1.1. 0 over 1.1 is 0. So the smallest I get is 0, which actually fits this point right here. That's 0, 0. When X is 1, Y is some value way up here. We probably hit, did I go from -100 to 100? I probably hit something less than 100. We got to substitute it, though. 15 times 1. Let's see, 15 times 1 divided by 1.1 minus 1. That's 15 over 0.1. Oh, that's 150. Never mind. I guess we never actually quite hit that x equals 1 yet. So we go to 150 for y. So y goes from 0 to 150. So we can remove as much as... Sorry, we can spend as much as $150,000 or as little as $0. I think that's my domain and range. That's what I'm going to go with there. So we're actually only looking within that box of values. I know we don't actually fit the true 150. Oh my goodness, that was not what I meant to do. I don't know if we don't hit the true 150 for y, but there's like a box that we fit within right here. All this negative stuff here and this negative stuff here doesn't actually matter. Part B says, how much does it cost to remove 20% of the pollutant, 40%, 80%? Does doubling the percentage of the pollutant remove double the cost? Explain. So let's figure those ones out. This one is kind of more so a table. Literally, we're substituting those values for x and getting values out for y. So that's totally cool. So substituting 0.2 for x, 0.4 for x, and 0.8 for x. Let's get those values. That's y equals, I'm going to use the table. Let's ask for 0.2. So it's 15 times 0.2, etc. But 0.2, 0.4, and 0.8. So it doesn't look like it's doubling, but 3.3 repeating. Some weird decimal, 8.5. That's actually, that might be 8.57 and 40. I was going to say that might be a fraction over this. This might be 4/7. It might be 8 4/7 is what we're doing there. I don't know for sure, but it might be. Anyway, so there are the numbers. Does doubling the percentage of the pollutant remove double? removed double the cost? Is that a typo? Does doubling the percentage of the pollutant removed. I see. That's not. Okay. Pollutant removed. I see. Does it double the cost? Explain. Well, no. It's not. This isn't a linear function. It's a rational function. Removing double the percentage does not remove double the cost. This is not a linear function. All right, that's where I'm gonna go with the problem. Sorry for going back and forth between whether I use the graphing calculator or not. Ultimately, it did, and I think that helped out in the end for me. Okay, numbers 47 to 50. Use a graphing calculator to graph the function, then determine whether the function is even, odd, or neither. Oh, okay. These questions, this is interesting because these are ones where I'd actually like to do it almost. Here's the thing: when I say without a graphing calculator, I'm not going to plot specific points outside of x and y intercepts, and if holes existed, and I don't think holes will exist here. You guys might not know much about holes. I might do a rough sketch of this graph and then use the graphing calculator after. So fair warning, guys, you can of course use the graphing calculator for these and go on your merry way with them, okay? I'm going to try and plot as much as I can with this. I'll make some small explanations, but this will go to the graphing rational functions. I'll tell you what, this is what I was going to state before. If you'd like to see more complicated rational functions such as these ones, and these aren't the most complicated, these aren't doing too much. They're doing something here and there. I'm going to point to something up there. Am I doing this right? Go up to that thing right there, and you can find a whole video on 8 more rational functions that we do things with. These ones, I'm digging myself a hole by choosing to graph these by hand if I do, but I'll go ahead and do it. Okay. I'll do it kind of quick. Number 47. The only thing is you're going to learn something new called holes on some of these problems. Honestly, I don't know much to do on this problem. There are no vertical asymptotes because you can't get 0 at all right here. Your horizontal asymptote, though, is at y equals 0, but this one's a little bit different because although it's what we approach over time, we can potentially cross it. And we can potentially cross it based off of the fact that, we can't cross this one because we'll always stay positive. Never mind. But it has a horizontal asymptote at y equals 0. Okay. So, given the asymptote, did I have a thin one before? Or was it this big? Given the asymptote, yeah, you know what? This isn't much. The y-intercept, you set x equal to 0, you get y equals 6. After that, as x increases, y decreases. This isn't quite that other form. So I could like plug in 1. 1 plus 1 is 2, and 6 plus that is 3. 2 squared. I'm kind of using a table on this one, I guess. But what I want to show you is just how this thing changes over time. When x is 2, then 4 plus 1 is 5. 6 over 5 is, like right there. This thing's basically just going to curve up here and then curve down and approach the asymptote from above here. And it is symmetrical across the y-axis, which helps answer a different question. Is this odd function, even function, or neither? This is an even function. An even function is symmetrical across the y-axis. Now, it said to use the graphing calculator, so I'll confirm that I get that answer from it. This was a little bit of a different kind of graph than the other ones we will be doing, I suppose. But 6 divided by x squared plus 1, I guess I can see why they didn't want you to do it. Let's get a normal looking... Actually, let's go even negative. You remember this? Negative 9.4, 9.4. Negative 6.2, 6.2. Let's square this thing off. So here's this graph. Curves up, curves down, does that kind of thing, right? So there's the graph. That's what I did. We got that. It's an even function. There's no vertical asymptote because there's no way that I can get 0 for x. I hope that you understand that. X squared, excuse me. There's no way I can get 0 in my denominator. X squared plus 1 equals 0. No real numbers can work there. Okay, number 48. Y equals 2x squared over x squared minus 9. And this one I can do a few more things with. So take a look at this one. As far as what I can kind of control. Let me start with the vertical asymptotes. This is where x squared minus 9 equals 0. X squared equals 9. Take the square root of both sides. X is plus or minus 3. Those are 2 different asymptotes, guys. We have 2 vertical asymptotes here. So we have this one and this one. I've sneezed. I'm allergic to double asymptotes. Okay, so we have those two. Horizontal asymptote. This is the same as was before. If these are the same degree, you divide the coefficients for the leading terms, 2 over 1. So your horizontal asymptote is as it was before for the previous ones. This is at y equals 2 over 1 or y equals 2. So I'm going to graph this one right here at y equals 2. Interesting. All right, intercepts. X-intercept. This is an interesting one. We've talked about polynomials in the past here, but 2x squared set equal to 0, divide by 2 and take the square root of both sides, you get x equals 0. But this has a multiplicity of 2, so this one's a little bit weird. There's an x-intercept of 0 right here, but expect a bounce-off feature for this. Don't expect it to go through here. Expect it to hit here and bounce off like that. That's where I'm not going to really plot many other points on this thing unless I played long division on it, which you could do a little bit of, and I can bring up. The y-intercept, you set x equal to 0. This is straightforward. It's also going to be 0 because you set x equal to 0, or the x-intercept is 0 like that. This tells me several things, okay, when it comes to these graphs. This tells me several things. This is the only time it crosses the x-axis. That means the graph is not going to hit here and here because it doesn't cross the x-axis here. I can expect the graph to go in these directions like so. I'm not plotting exact points. I'm just giving you behavior. Exact, like so and like so. This thing already has a lot of symmetry appearing right here around the y-axis. It goes left and right 3 units, and it hits 0 as an x-intercept. And like I said, it'll have bounce off right here, and it'll go down in this direction. It won't. There's a possibility of something crashing through asymptotes in some sort of ways, but not to deal with this one because of the x squared. This is my expectation for a graph like this. I'm expecting even. If there's anything that you can do with this, it is based off of plugging in other numbers. This is where you would get deeper into long division. I shan't spend too long on this here, but doing long division, x squared goes into 2x squared 2 times, and you get 2x squared minus 18. Add that, you get 18 here. So you get an equation that can be rewritten as 18 over, hold on, actually I like to write the quotient here first this time because it's not in that other form. 2 plus 18 over x squared minus 9. Here's what this is saying. From 2, we're going to add or subtract certain amounts from here. And when x is a number between -3 and 3, this becomes a negative result. If it's a negative result, that means it's underneath this right here. It's at least 2, it's going to stay underneath here like this. When x is a number greater than 3 or less than -3, this becomes a positive number. Becoming a positive number, adding to 2 means we stay above. So I fully believe this graph will be as it is. It's okay if you didn't understand any of that because I went quickly through it. But let's go to the graphing calculator. Let's confirm that that's the kind of graph that we get. We're going to get 2x squared over x squared minus 9. And take a look. So, like that. They don't draw the asymptotes, right? Whatever you saw before was just a mistake on their part, but there is the graph. It looks like an even function to me, and that's what we're getting. Okay, number 49. Now, 49 is not written in standard form on the bottom. X to the fourth is bigger than, x squared when it comes to degree. So just be careful with that. In fact, if you don't mind, I'm going to do a rewrite of this right now. X to the fourth plus 3x squared like that. Okay. This one is something new that you haven't learned before. So this is where I have a common factor of x squared on bottom. And then I'm left with x squared plus 3. I can now divide out whole x squared from here and 2 x's from there, and I'm left with x over x squared plus 3. But, and this is the same graph as this one would have been, but with one exception. There is a hole in my graph. A hole appears when you divide 0 by 0. And if I plug in 0 for x, I would have gotten 0 over 0 here. So I have a hole at 0, and then the y value will be 0 as well when I substitute 0 into here. A hole just means a place that it also doesn't exist like asymptotes, but it doesn't approach positive or negative infinity. It approaches a value. It's going to approach 0 very closely on this thing. Now, this thing does have no vertical asymptotes given the x squared plus 3 nature. It has a horizontal asymptote of y equals 0 because the degree on bottom is smaller. So again, I'm going quickly through these because they expected you to use a graphing calculator. So I'm just showing you, hey, I can still get the same graph out. There are some points I'd have to plot here just because the x-intercept can't be 0 because there's a hole there. A hole is just basically drawn like this, and the y-intercept would also be 0. So I would have to plot some points on this thing. I just know that as x becomes positive, if x is positive, I get positive numbers. As x is negative, I get negative numbers. So really all I know is the hole and the asymptote. There isn't really much more that we know to this graph unless we plugged in values. If I plugged in 1, I'd get 1 over 4. If I plugged in, I don't know, -1, I get -1 over 4. So you're not going to get very pretty numbers based off this. I'll tell you that right now. If I plug in, yeah, let's see what the graphing calculator says. But basically, it's going to jump up here somewhere and then go approach the asymptote like that after, and it's going to do the same thing on that side. I don't know how specifically, but it's something like that. So let's go to the graphing calculator and do this. These are the weirder versions of the graphs. So apologize that I even gave them a shot here to begin with. This thing might not show the hole, especially since it's on an asymptote. Excuse me, especially since it's on an axis. X to the 4th plus 3x squared. And you got to graph the original. So it does that. It does what mine's doing. I have to zoom in more so we can see more features of it. But no, it doesn't do the shoot up and shoot down like mine did, but it approaches something and it would end up going back down to 0 over time. So my graph's kind of close enough. But the point is this is actually an odd function. This is an odd function because it's symmetrical across the origin there. Okay, number 50. I kind of regret doing the extra bits that I'm doing here. I'm still working on it. I just regret it. Just because these aren't the kinds of graphs that I expected out of these. Some of these can get... I think the 2 asymptote one was good. This one actually might have 2 asymptotes. 2x cubed minus x. So this one here, again, I can factor out... You really want to play with the factorization here. I can factor out an x on bottom. And I get 2x squared minus 1. Now, here, you can cancel an x, boom, boom, like that, and then you're left with 4x over 2x squared minus 1. From there, we can do some more work. Now, that being said, there is a hole on this one, also at 0, 0, because you plug in 0 for x into here, you still get 0 out for y. Hole at 0, 0 like it was before. So we'll make sure to note that it's not one of your asymptotes. We look to this set right here for your vertical asymptotes. Regarding vertical asymptotes, 2x squared minus 1 equals 0. Add 1 divided by 2, take the square root of both sides. 2x squared is 1. X squared is 1/2. X is, plus or minus square root of 1/2. I don't know. The numbers aren't great, right? So when it comes to my graph stuff, that's what? Square root of 1/2 is 0.707 or something like that. I remember those numbers from 2 root 2 from trig. So it's like 0.7 and negative 0.7 if I thin it out. Not great numbers, but probably an even or odd function all the same because there's symmetry on this thing. So kind of here and there. Y-intercept, horizontal asymptote. The denominator degree is bigger, so that'll be at y equals 0. Horizontal asymptote at y equals 0, and I can draw that right here. We have a hole at 0, 0. So it does actually cross through this thing somehow. Maybe it bounces off. I'm not really sure. We can do some more things through division just because there are no intercepts. So these are the trickier of the problems. With no intercepts, you're going to have to do more work. I'd have to do like long division on this thing. 4x over 2x squared minus 1. Oh, you can't. So you from here, you just plug in points. I mean, listen, just look at sign changes. When x is positive, y is positive. Because that's positive over positive there. So you get positive numbers here even from that side. When x is negative, no. When x is positive less than this thing, it's probably smaller. When x is like 0.5, you get 2 over... 0.25 is 2 minus 1. That becomes a negative value. So when x is positive but less than this 1/2-ish value, the square root of 1/2, it becomes negative. When x is negative right here, it becomes positive. I guess this is why they're using a graphing calculator. When x is positive bigger, it becomes positive here. So it approaches like that. And again, I'm not plotting specific points. It's doing whatever. And then here it's doing this on this side. It appears to have symmetry as it would have before. This is what would happen here. Sorry for... I'm not saying too much on it. I probably should have just followed their thing and used the graphing calculator. I kind of regret. I should have reset this whole thing. But I'm doing 4x squared. Go to the calculator now. I'm doing 4x squared over 2x cubed minus x. I guess the point is there are different kinds of graphs that can be really funky looking, and you're seeing them here. Oh, let me zoom out. Okay, so you're seeing what I saw here before. Unfortunately, they make versions of asymptotes that are not really there, but you can see the curve there and then the curve through there. That's the point that we're making there. That's where mine kind of shows it a little bit more. It even shows the whole. This is an odd function. This is an odd function. So nothing looks like a neither here. All right. Sorry. I did what, well, sorry, not sorry, right? The graphing calculator can only show you so much. I'm sure Desmos or something would be a better version of that, but using the TI is a little weird. Your friend claims it's possible for a rational function to have two vertical asymptotes. Is your friend correct? Justify your answer. You just saw it. So yes. Yes, right here. Yes, basically you need multiple values of x that can get you 0 in the denominator. C number 48 and 50? What were they? C number 50 and number, 48. There's the justification, but me explaining how. This is possible when the denominator has multiple values of x for which you would divide by 0. So we saw just instances of that previously, especially when you have a quadratic, something like that, a higher degree. When x is an x squared, x cubed, you have a better chance of doing that. Not always, but you have a better chance of it. Number 52 says, use the graph of f to determine the equations of the asymptotes and explain. We're looking for what we're approaching here, and it looks like we're approaching this guy and this guy here. I don't have much of an explanation. It's just based on approach and symmetry, really. If you think about how far over you go, and like I go 1 over, I go 5 down. If I go 1 over here, I go 5 up, and it seems to have that symmetry, that kind of thing. So vertical asymptote is x equals -3. Horizontal asymptote is y equals 2. There appears to be symmetry around these lines and approach toward these lines. Okay. Number 53. Maybe these are faster. Drawing conclusions. In what lines is the graph of y equals 1 over x symmetric? What does the symmetry tell you about the inverse of the function f of x equals 1 over x? Oh, so, well, we've drawn this plenty of times from the start. You know, these are the ones where, I don't know if I have this graph paper copied anymore. But this is where we, 1 over x is literally just most basic form of this stuff here. Divide 1 by 1, you get 1, and then, a half. Divide by 2, you get a half. Divide by a third, you get 3, etc. But think about that. Divide by 2, you get a half. Divide by a half, you get 2. Divide by a third, 3, you get a third. Divide by a third, you get 3. Divide by 4, you get a quarter. Divide by a quarter, you get 4. You're getting the opposite x's and y's. X's and y's flip. When x is 1/4, y is 4. When x is 4, y is a quarter. Things like that. And it same is true on the other side. -1, -1, -2, -1/2 versus -1/2, -2. -3, -1/3 versus -1/3, -3. -4, a quarter versus -1/4 and 4. So it does the same thing on the other side here. X's and y's can trade places. There is symmetry on this thing, like an inverse function would. That's why they're asking about it. But there are two forms of symmetry, actually. I see one that's across the line y equals x, which would be the one I was really thinking about to begin with. So there's this line here, y equals x. If you tilt your head that way, you can see the symmetry. There's also the line, though, y equals -x. How about this one? This one seems to have the same kind of symmetry. If I flip it like that, there's symmetry across that one as well. Y equals -x. It reflects across those lines. So in what lines is the graph of y equals 1 over x symmetric? It's symmetric across... Whoa. y equals x, and y equals negative x. It says, what does the symmetry tell you about the inverse of the function? The inverse of the function is really based off that first reflection that we said. The inverse of the function means it's the exact same. It means the inverse is the same if it can reflect across that. The inverse is the same. Now, if you want to check that out, we start with f of x equals 1 over x, turn x into y, or turn f of x into y, swap x and y to take the inverse, and solve for y again. Multiply both sides by y, divide both sides by x, and then you have your inverse. So these are the same. The inverse is the same. Boom, boom. Okay. Itchy. Number 54. There are 4 basic types of conic sections. Oh, I brought this up earlier. You probably haven't done them yet. Parabola, circle, ellipse, and hyperbola. Each of these can be represented by the intersection of a double-napped cone and a plane. I guess we're not going to speak too much about that unless they force us to. The intersections for a parabola, circle, and ellipse are shown below. Sketch the intersection for a hyperbola. Honestly, without me knowing, like, if I didn't know the answer, I don't know, maybe I'd have trouble with it. Because I do know it, I can do it. I got to find a way to make this show without, I don't know, do I have to draw my own cones? I have a spider in my room. And it's standing out quite a bit. I'm going to draw my own cones. So I'll have a cone here, the inversion of a cone down here. The hyperbola is a vertical plane cutting through this thing. So imagine that you had, I don't know how to do this best. I'm going to try and, I got to makeshift this thing. Imagine that you had a plane cutting through vertically, basically, is what's happening. So I'm going to do it like, imagine this thing cutting whoosh through like that. I don't know if this is going to make much sense. But I'm cutting through vertically right here, and the cross section, which we've spoken of before, hits this and hits this right here. This is the hyperbola that we're talking about. We're doing these for all of our problems as well. Ooh, that's not quite vertical though. Let's try that again. There we go. There's vertical. Let's get it closer to here so we can do the cross section again. Our cross section, I'll do it in blue. I don't know. You have to understand the 3D aspect of this thing. But there's that version there, and there's that version there. They need to be symmetrical. I think that's kind of what they're hitting at, so that's why they need verticality. And it needs to go out both directions for it, whereas all the other ones don't necessarily need to do that. All right, number 55. The graph of the rational function f is a hyperbola. The asymptotes of the graph of f intersect at 3, 2, and the point 2, 1 is on the graph. Find another point on the graph, explain your reasoning. Well, they're probably going to talk about a reflection piece with this. I could come up with the entire equation for you, I'm sure. But let's just get into what they have here. They have the intersection of the asymptotes at 3 and 2. That means x equals 3 and x equals 2 are your asymptotes. So x equals 3 and y equals 2, I should say. These are your asymptotes. Boom, like that. Now, the point 2, 1 lies on the graph. So here's 2, 1. That means that, well, the a value is 1, I could tell you that. But that means there's another point right here. There's a point right here also that's 4, 3. That's symmetry about this thing, right? So 4, 3 should be another point because symmetry. If you want a whole equation, your a is 1 over 1 up 1. Your whole equation would be f of x equals, it would be 1 over x minus 3 and plus 2. Those are the asymptotes, 3, 2. Or, x equals 3, y equals 2. And then a thing of 1. So you can find any other point. I could give you another one right here and, things like that. All right, number 56, abstract reasoning. Describe the intervals where the graph of y equals a over x is increasing or decreasing when a is greater than 0, a is less than 0. Explain your reasoning. So it doesn't matter what it does if a is positive or negative. But when a is greater than 0, when it's a positive number, actually, let's do generic graphs. When a is greater than 0, we're looking at graphs that do this, positive. And when a is less than 0, we're looking at graphs that do this. Now, let's keep in mind what we're talking about here with regard to intervals where something's increasing or decreasing. Increasing is based on as x as x increases, what do we do as x decreases, etc. So as x goes to the right, this graph is decreasing, and as x goes to the right, it still decreases. It doesn't ever hit 0, but this one decreases on all intervals except 0. Decreases where it says intervals, so I can't just say x can't equal 0, but I'll go from negative infinity. Well, I'll just say x is less than 0 and x is greater than 0. It decreases the entire time. It goes down here, and then it goes down here, and there are no values at 0. This thing increases the entire time. It increases when x is less than 0 and when x is greater than 0. But it increases the entire time. It's going up here, and it's going up here, just from a different spot. But it never has a value at 0. Number 57, problem solving. An internet service provider charges a $50 installation fee and a monthly fee of $43. The table shows the average monthly costs Y of a competing provider for X months of service. Under what conditions would a person choose one provider over the other? Explain your reasoning. So let's come up with an equation for this other one here. Not the table one, but the information. The $50 installation fee and monthly fee of $43. And we're talking about X months of service. So it's one of these again. Average monthly costs, and let's compare them to this other one. So I'm going to go to the graphing calculator. I'm going to get this, and it's not really about the graph this time, it's just about the table. So 43x plus 50 divided by x. Now the other table uses months 6, 12, 18, and 24, so I'm going to do the same thing. 6, 12, 18, and 24, and I just want these 4 numbers here. That's all I care about right now, just those 4 numbers for y. So I'm going to go ahead and paste them in right here. And let's compare it. Let's compare the things, shall we? So at 6 months, my average cost is better for the competing provider. That's better. And better and worse. So somewhere between 12 and 18 months, the competitor, it changes, right? This becomes cheaper, and it should become cheaper over time. Now it only narrows to $43, right? I don't know what the other one narrows to. Probably 45 for all I know. But the first ISP, let's see, the competitor is better for months 6 and 12. I don't know when they changed though. And the ISP, I don't know, is better for months 18 and 24. Now, we don't know the in-between because we don't know what this actual function is. Maybe there's one we could figure out, but I'm not going to sit around and find out. So those are the only numbers that we have, and those are the conditions. All right. Is this our last question? It is. Three parts, but number 58. Ooh, there's a lot. The Doppler effect occurs when the source of a sound is moving relative to a listener. So the frequency f sub L in hertz heard by the listener is different from the frequency f sub S in hertz at the source. That's true. It's like the, I don't know, and kind of, goes away. I don't know if that sounds the same to me. Anyway, I'm not good at car sounds. In both equations below, R is the speed in miles per hour of the sound source. I'll trust it. Let's see. F sub L equals 740 times F sub S over 740 plus R. I'm like shaking over this problem, going like, oh my gosh, what are we going to have to do? So this is moving away. And this is approaching. So there are two different ones. When you approach, you have a different kind of model. F sub L equals 740. Oh, it's just plus versus minus R. I see. F sub S over 740 minus R. Okay. R is what? The speed in miles per hour of the sound source. Part A. An ambulance siren has a frequency of 2,000 hertz. Write two equations modeling the frequencies heard when the ambulance is approaching and when the ambulance is moving away. Well, now we're substituting 2000 in for the source one, right? That's F sub S at the source. So part A, you have the moving away one is F sub L will be 740 times 2000 over 740 plus R. I'll have to calculate that in a bit. And approaching F sub L equals 740 times 2000 over 740 minus R. 74 times 2 is 148, so this will be, how many zeros? 1480000. And same thing for minus R. Okay, so that's part A. That's the moving away and approaching. Part B, graph the equations in part A using the domain from 0 to 60. So let's go. I got to use X instead of R. All right, we're going to go from 0 to 60. I have no idea what kind of Y values we'll hit. Let's see. Oh, they probably got to be big, huh? Let's go, like, probably not negative. Let's see what 740 brings us, even. Whew, I have no idea where these values are. They might be bigger. Well, the times 2,000, right? It's going to go bigger. Let's go up to 4,000 and see what we get. Oh, there's something. Oh, okay, interesting. So let's see. I'm going to change the Y scale so we get a lot less within. I don't care about things under, say, 1,000. Let's go 1,000 to 3,000 and see what's going on. They didn't say how Y needs to look, just how X needs to look. A little better. I think I can get a lot closer, though. 1,500 and 2,500. All right, that looks a little better. All right, so graph the equations using the domain. So I'm going to use this one here and just kind of note what that range is. That's from 1,500 to 2,500, right? So graphing calculator. Definitely was not about to do this by hand. Sorry. So part B, this is 0 to 60. That's speed, by the way. This is 1,500 hertz to 2,500 hertz. Now, one of them is, oh, I don't know which one's which. One of them plus R. I'm going to redo the graph things. I'm going to make one bold. Hold on. I need to tell which one's which. So the plus R is this one. This is moving away, and this is approaching. And that makes sense. The frequency increases as it gets closer. Yeah, that totally makes sense. Okay. Part C. For any speed R, how does the frequency heard for an approaching sound source compare with the frequency heard when the source moves away? So this kind of answers the question. The frequency heard is greater for an approaching sound source. So for any R, right? Because they're the same when R is 0. Like, you know, the object's not moving, whatever. So the frequency heard is greater for an approaching sound source. And then as it goes away, then, right. Good old Doppler and his effect. We figured it out there. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Definitely one of the longer ones there. I don't, hopefully the other things we are going to do more algebraically, they make more sense. We're going to have to do things on factoring, I do believe. Things with fractions, right? Common denominator, things like that. But things algebraically, I think, will make a lot more sense here than what we did before. So apologize on the more complicated rational functions one. I tried to do them by hand. I kind of did, but they weren't actually the kinds that I expected just because there were never any x and y intercepts. They never really hit anything for us. Always holes, which was interesting. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Take care, and I'm going to see you in the next one.